Thank you all for joining this meeting. Welcome everyone. Good morning, good afternoon, and good evening. Thank you for joining the roundtable, Digitalization for Asset Reliability and Integrity in the Petrochemical Industry. I am Abdul Mohsen Ashali. I am a materials engineer at the Saudi Basic Industries Corporation, SABIC, based in the Kingdom of Saudi Arabia. It's my great pleasure to chair this event along with the Executive Director of the Material Technology Institute, Paul Whitecraft, and the Director of Operations, it would be our pleasure to invite Mr. Mohammed Al-Hassani, the General Manager of the Asset Technology Center of Saudi Basic Industries Corporation, to deliver a welcome remarks and support. Ali, the floor is yours.
Assalamu alaikum. Good morning to all. Good afternoon for others. I'm Mohammed Al-Hassani. It is a pleasure and privilege being with you here today with such important platform. We see our colleague and partners at MTI with this important platform that will help and definitely benefit the whole industrial or the petrochemical industry. We are privileged being a member in this, let's say, MTI Institute, and despite all the challenge we are having now, I think there is good intent from all the stakeholders to conduct this roundtable. As you know, digitalization is a very important subject that it should help us when it comes to our asset integrity and reliability, and hopefully that will take us to the next level. Capitalizing on the technology is one of the enablers that we are looking forward and learning from each other, understanding the challenge in the industry, working together as usual as a partner. This will help in mitigating the challenge as we are going. I urge every one of us during this platform to share the experience, to share the practices among the organization that hopefully will help in being more reliable and definitely safe when it comes from asset perspective, so we can be more safe, and this will help the whole community, not only the industry, including the community surrounding us, being reliable and being safe. We're looking forward for more fruitful engagement with the community of MTI and other team members here, and I'm sure and confident that you will take us to the next level. Thank you very much for inviting me. I don't want to take from you too much time. I know it is early morning and also maybe late for some people. So I wish you all the best. We'll stay with you until maybe for 1 hour. And I wish that I can stay all the time, but I'm engaged in other meetings. So excuse me to stay only for 1 hour with you today. And thank you very much.
Thank you. Thank you. Thank you very much. Mr. Paul Whitecraft would like also to share some welcome remarks to the audience. Paul, the floor is yours.
Thank you. Good morning, good afternoon, good evening to all of you. I am Paul Whitecraft. I'm Director of Executive Director of MTI. I joined MTI about 4 years ago, but prior to that, I had been with both Carpenter and Rolled Alloys for a number of years with MTI. We're very grateful to be using this platform today to share with you this roundtable on digitalization. Abdul Mohsen Al-Salih of SABIC has done an excellent job pulling this together. We're very grateful to them, and we're thankful that SABIC has been a member of MTI for a number of years and made some great contributions to our community. I'd just like to take a few minutes to tell you about MTI if you're not familiar with us. Our goal is to maximize our members' assets by providing global leadership in materials technology. And we do this to improve sustainability, reliability, and also the profitability of your organization. We are 64 members, 64 member companies. We are worldwide. You can see that in the Middle East, we only have SABIC as a member currently, so we're certainly interested in growing our membership, and hopefully this will be an introduction for you as far as MTI. We work with our members in a number of different ways. This is a very collaborative effort. It's driven by our members. We work in the areas of research and development by generating projects that are member driven. We do a lot of training and education, such as what we're doing today. And one of the biggest benefits our members often report is the ability to network with leading industry experts around the world. We have several project development committees that focus on certain areas of materials technology. So these groups develop projects by the members, and we fund these projects through the members' dues. We focus primarily on ceramics, polymers, metals, but we also do carry on efforts in knowledge management and the prediction of materials degradation and integrity and condition assessment. So we're looking not only at constructing equipment, but also managing it and maintaining it during its service life. We spend typically over $750,000 per year on these member-driven projects. We currently have 17 active funded projects. And in 2020, this year of COVID-19, we have still managed to fund 10 new projects. And we've also completed 8 projects this year so far. So even in the midst of the coronavirus, we have been very active. We've had a number of meetings. We learned how to do virtual meetings, and our members have benefited very well, even though these are trying times. I also want to mention one of the areas that our members greatly appreciate. We have an online technical forum that our members can post questions, and it's typical that they get a response from one or more of our members in less than an hour. This is available 24/7, so anywhere around the world, you can post a question and begin receiving expert advice that is shared by our membership. I'll close here. I don't want to take up too much of our time either. You can email me if you've got questions. I'd be happy to take a quick question if we have a few minutes now. You can use my email address, or if you go to our website, which is mti-global.org, you can also post a question on our Ask MTI section of the homepage of the website, and we'll get back to you. So Abdul Mohsen, thank you very much for your excellent job in putting this program together. Thank you for coming to MTI to use us as a platform to share your information, and I'll let you take it away. Thank you.
Thank you, Paul. Thank you. Thank you again, everyone, for joining the roundtable. The topic we are going to talk about right now is one of the most consistent topics that comes up in conversations nowadays. Typically, there are 3 broad angles on this that companies around the globe are wrestling with. The first is how they rewire themselves to take advantage of digital cloud-based mobile-oriented world, and how they leverage advanced technologies like artificial intelligence, blockchain, robotics inside their organizations. The second is how they leverage the massive amounts of data out there and really be able to bring advanced analytics into their business, and not just bringing it in algorithmic sense, but bringing it in human sense, the way to implement this, the people that have the capacity to use it, and so on. The third is how do they use this digital world as a source of innovation to bring competitive advantage to their stakeholders and to their customers. To address these questions and more, we are hosting a group of fantastic people, very well distinguished subject matter experts, to deliver these topics and to enrich our discussions today. We will have this conversation in blocks. We will start by defining what digital transformation is. Then we'll talk about advanced analytics and applications for advanced analytics to improve reliability and integrity in the petrochemical industry. During the presentations, you will have the chat option, so you may utilize that platform to ask questions, and we will take those questions afterwards to the presenter. You also will have the chance to ask after the presentation, but we encourage you to post the questions in the chat during the presentation. Our first presenter will be Mr. Robert Ohms from Becht Engineering. Robert Ohms is the Strategic Business Planning Director of Becht Engineering. Mr. Ohms will speak about digital transformation, about practical insights into framing and realizing value from digitalization journey. Thank you, Robert, for accepting our invite, and the floor is yours.
All right. Well, thank you very much. I appreciate the opportunity to be here today. Hopefully everyone can see the screen and the presentation. Joining me today as well are two other members from Becht, Charles Becht V, who is our president of our engineering services group, as well as Sridhar Srinivasan, who is within our corrosion materials group, is here as well. So available to answer any questions not only in this session, but in the others as we go forward. And a little bit about Becht for those who may not be aware. Becht was formed in 1964 to serve the global energy industry. We work within the refining, petrochemical, renewables, and power portions. Our core mission is to help our clients succeed, and we do this in a wide range of ways. We have over 1,500 global employees, with 90% of those who have spent time with an owner-operator at some point in their career. We also have deep participation in forums like MTI and in developing of codes and standards. And so our typical approach involves providing detailed technical analysis, expertise, and guidance to help solve our clients' most difficult problems. So as mentioned today, we've got a great lineup of presenters, and our focus is really taking a bit of a broader view on the digital transformation, what it means, and what it might involve for you. So with that, what we'd like to cover today are some learning objectives. We'll go through some various definitions that are available on what digitalization actually means, and then share some learnings that we've experienced in our own involvement of a digital transformation, not only within Becht, but in working with clients in the industry. And then wrap up with a few recommendations and thoughts on how to move forward. So for the learning objectives, again, the goal, I think what we're all trying to achieve is a successful digital transformation. And For us, it really involves three main areas. The first is identifying those value generation opportunities that digital transformation and digitalization will enable you to do. The other is to address the work processes and the organizational elements. I mean, obviously the tools, the technologies are very important, but these two elements are quite critical in order to achieve the success that you're looking for. And then the final is applying some different project management techniques, and we'll touch on each of those today in the session. So let's start with some definitions. And if you go out and do web searches, or many of you have been involved in this, there's a lot of different terms tossed around digitalization, digital transformation, what it means. For some people, it's a 3D scan of their facility. For others, it's the application of machine learning or AI technologies for analytics and decision making. For others, it's a digital twin. So it's that mathematical representation of the physical asset, the processes, the equipment, and actually all the above are right. There is almost no wrong definition, but there are several out there that you need to keep in mind when you're talking with providers and other entities about digitalization. Now within Beck, this is really our way of defining digital transformation, and I won't read it verbatim, but fundamentally it's about aligning the work processes, the staff, and the technologies to achieve the goals that you want to in your entity. And that will be our focus of our discussion today, of these other elements around the people, the processes, and the technologies. So the first part is really understanding what are those value improvement opportunities that are out there for you. And if you look at ways to improve your and achieve your return on capital employed, it's several different elements, right? You can either work on reducing your costs or increasing your profit margin, achieving and sustaining reliability, as well as maintaining that license to operate, with now a lot of entities requiring some type of a sustainability, green type of initiative within that. So when you go about trying to identify some of these potential value improvement areas to apply some of the digital techniques that are out there, the first area is to try to find where is there value leakage within your system. And what do we mean by that? Well, looking at this chart in the bottom left, these are just a few potential ideas. But if you look at the data and the information flow within a typical facility, it might be something like inefficient communication between the various groups, or within the planning part of the organization, having inconsistent constraints. Maybe there's siloing of data. Data is not as readily available and at people's fingertips as much as they would like. Or maybe there's a lack of equipment availability within the operations team. So all these are potentially valuable areas to look into. And when we look for avenues to generate value, a great way to do this is to engage the frontline staff, because they're the ones who day in, day out are looking at your asset and that operation and the health of it, and can oftentimes identify those improvement areas. What they need is some help and funding in order to achieve that improvement, hopefully with digitalization providing that. Once you've identified some of this value leakage opportunity, then you can start to work backwards to develop and understand where digitalization can help transform your organization. And it's definitely not a one-size-fits-all. There's going to be different applications and different areas of value improvement for each of the entities out there. But by engaging the frontline staff, you not only get great ideas, but it's buy-in, because they're oftentimes the staff that will have to use the outcomes or some of the tools that are available. So when you look at digital transformation, a lot of it is very rightfully centered on data. And we as humans, especially in times of uncertainty, oftentimes think, well, if we have access to more data, we can make better decisions. And that may be true, but it's really the right data. And a recent article within The Economist provided a statistic from a market research firm that 80% of the time of a typical AI project involved data conditioning. And that really struck me as an important piece of information, because taking a look at your base data quality. Do you have the right data in the right location at the right time? Is going to be an important element to look at pretty early on in the process. Because if you want to be a data-driven organization, which is really what this is all getting back to, you've got to have good data to start with. But an important element to remember too is that you need the talent. And what do we mean by that? Well, what we mean is that you can have all these great ML and AI applications and other elements to generate knowledge, but you need that talent to really disperse that within the organization, understand what do I do with the analytics that become available. And because the ultimate goal is you want to get your staff away from that base data crunching and really in using the information that's generated from this. So you create, as we're terming here, this single version of the truth. Now, this is a case study where we were working with a client. It was a North American refiner who was looking at their condition monitoring locations as part of creating corrosion control diagrams and the associated damage mechanisms. This particular facility in this process unit had over 7,000 condition monitoring locations, and they wanted to make sure that these were all the right ones to do. So by applying some of the best practices that we have within BECT, as well as the client's own standards, we were able to reduce the number of locations by around 70%. And that's pretty substantial, because if you think about not having to deal with all those additional locations that may actually not be giving you any better fidelity and understanding of your asset, now you really can focus on those key pieces of data that will really give you knowledge within your facility and help with your decision making. So again, one of our recommendations would be do that data quality review to understand, do you have the right data? Do you have the right information available to you? The other areas to focus on beyond the tools are the people, the processes, and the culture. And as we talk about here, digitalization is not just an IT initiative, and obviously IT is very critical to this whole piece. But in many organizations, it's viewed as that. And when you have that kind of a mentality for digital transformation, you may not achieve the successful outcomes that you're desiring. In addition, it's got to come from all sides. You know, the frontline staff are going to be the end users of a lot of these, so they can help with the generation of the opportunities, but they should also be involved in the development. But you also need the support of senior management. They need to see this as one of their core strategies and elements that they're trying to implement. So if it's kind of pushed aside and ignored, it's probably not going to achieve the outcomes that you would really desire. One of the other firms out there by the name of New Vantage did a survey talking to executives that were part of becoming a data-driven group, and 48% of the executives cited people as their biggest challenge and biggest barrier to becoming data-driven, and only 19% of it was technology. And that's something to keep in mind as you go through this. Is this, like any other organizational change, is going to have to impact the people. You're going to be impacting their jobs, what they do on a day-in, day-out basis. And when you look at these, it's important to take a fundamental look at the work processes. Trying to put a tool that you develop or some technology or advanced decision-making into a broken process is not going to achieve the results you want. This is your fundamental time to rewrite and improve those work processes, get the people involved in that so that they have buy-in and really well implement this. We saw this with one particular client that was trying to implement some dashboarding for an operations team. And unfortunately, it became more of an IT and a technical team type of a project that didn't even really engage the operations staff. So what happened when they rolled this out is they just didn't buy into it. They didn't see the value. They didn't see how it improved their job and their decision making. And it didn't work out as well as they would like. So again, make sure and engage all the right parties as part of your particular pursuit that you're looking at. Another area to look at is be agile, be concise, and avoid complication. Now, obviously, there are a lot of very advanced techniques and technologies out there that are will certainly enable your digital transformation, but sometimes it's also just doing something with the data and the tools that you have. So one particular example that we had was we were working with a client that was trying to better understand the drum life of their coker unit. And as you know, oftentimes in a refinery, the coker is one of the most profitable units in there, and understanding how long that you can run that asset and what the variables that you can run it at to achieve the safety, reliability, and profit targets are pretty important. So we work with them doing some advanced analytics to drive down to the 8 key pieces of information that really decide the life of that coke drum. And they were able to utilize that not only within one of their facilities, but adopt it as their standard. And again, it takes this heavy lifting of really working with your staff to do the analytics, to define the value that can be achieved with digital transformation. And when you do these, oftentimes there's a lot of these trials that'll be done that are very important, because if it's working, you want to keep doing it and make it a sustainable project. But oftentimes it's good to actually fail quickly. And that's one of the advantages about using some of the agile project techniques, project management techniques like sprints and scrums and Kanban and others that are out there, is if it's going to fail, you'd rather know about that sooner than later before you invest thousands and sometimes hundreds of thousands of dollars in some of the initiatives. Another example of a case study, we were working with a client who was trying to enhance their knowledge capture and dispersal, especially in between their technical and operations teams. So as part of our platform, we developed what we called interactive control diagrams. And I know it's a little bit hard to see here on the screen, but what this was is essentially a simplified PFD that showed not only the control points for a particular unit, but also integrated things like the corrosion control diagrams and damage mechanisms, operating best practices, process technology best practices. Having that in all one platform that everyone could access with wiki searches and keyword searches, it was a way to not only bring to bear the information that the client had already developed, some best practices that we could bring to bear, but a way to make it evergreen. And as most of you know, a lot of the new staff that are entering an organization grew up with information at their fingertips. They had Google to do that search. And so they're always striving to have that kind of ready-made data access. These types of platforms can be definitely part of your digital transformation in order to capture that information, but also make it easily accessible and in a way that your users are used to having as they work. So as we start to wrap up here, before we turn it over for some comments, questions as we go through, a couple of additional recommendations. So for some of you that are maybe starting down digital transformation and digitalization, again, as we've talked quite a bit about in this session, this is really the time to look at your data and understand your data gaps. Do you have all the right data and information? That may be process, laboratory, equipment, condition, whatever it might be. And there are times where you can use synthetic data that's out there, but again, be careful doing that. You don't want to have so much synthetic information that you lose touch with the reality of that particular asset health and operation. The other element is, again, to engage your staff to brainstorm where are those quick win opportunities? Where are those ways that we see value leakage somewhere within our system that we can extract more value? Work with your frontline staff as well as your technical providers, the IT group, as well as your senior management in order to create those agile pursuits for you to implement and trial some of these out and make this a sustainable part of your digital transformation. And then the final one, and this really applies again for anyone who is doing this, is don't just focus on the tools and the techniques. They're great and they're fantastic, and they'll certainly provide you the value that you're looking for. But you really also have to do the improvement of the underlying work processes, the development of the people. Again, their jobs are going to change. They'll be doing things quite differently than they did before. And for some staff, this can be a very concerning time that they worry, well, will I be losing my job? Do I have the right skills in order to leverage this? So this is the time to upskill and train those particular staff, not only in the tools and the usage, but what to do with all that information and knowledge that's being created. That is some of the gaps that we see out there oftentimes is great information and knowledge that's created, but people aren't quite sure what to do with it. We saw a particular application where it was predicting some very valuable information on equipment health, but there wasn't that understanding of what do we do next? Do we shut the kit down? Do we change the process? Do we change what's flowing through that particular equipment? So having that element worked into this as well is critically important. So again, thank you to MTI and to the attendees today for the opportunity to speak. At BECT, we're always available to assist clients not only in their digital transformation, but also being a trusted advisor throughout whatever improvements that you're looking for. Again, we do come from an owner-operator perspective and over 1,500 subject matter experts to assist you on a global basis. So at that point, I'll open up the floor for any questions and also try to see if I can find the chat function to see any of the questions that may have come up in the session.
Thank you, Robert, for a very informative presentation. Very practical insights indeed. So this is now the time for questions. So if you have questions, please feel free to address your questions to Robert. You may utilize the chat platform, or you may write in the chat platform and we will unmute you. Please try to, if you are posting a question in the chat, to mention the name of your company.
Well, and if there are no questions, we're available the rest of the day. Both myself and Charles and Sridhar will be available and happy to chime in as well.
Actually, Robert, this is Byron with MTI. I just had one question.
Sure.
From start to finish, how long does one of these processes take? And, you know, what are the steps that you take in the beginning as far as, do you get an implementation team together and, you know, all of that kind of step by step in a sense? Is how long does it usually take to start to finish on this?
Yeah, it's a great question, and you know, honestly, it depends on the type of area that you're looking at, and you know how involved that's going to be. Most of the sprints that we've seen are typically, let's say, maybe about 3 to 6 months. Some of them can take upwards of a year in order to do them. A lot of it depends on, again, how broad you're going after some of these particular initiatives, and also the baseline quality of your data. We found some of the clients kind of jumped in headfirst into developing some of the tools and techniques, and pretty quickly realized they didn't have sufficient data. You know, for instance, oftentimes a stream may only be sampled a couple times a week. So how are you going to make some decisions on something that you only get a bit of a snapshot on? So a lot of times the heavy lifting that has to be done is in that first review of the data conditioning. That can take weeks, sometimes months for that to happen. But again, we do try to recommend that if you can put together that small enough of a sprint and a focus to try to get a quick win, build on success, and build that out. So hopefully that helps us some context. And I'm sure the other providers today will give some first-line experience what they've done as well. I guess one of the other questions that came up of issues with getting information to your more seasoned engineers. I don't know if that was for me or for the group, but happy to try to answer that one as well. Yeah, and that's one of the things we see, especially as we've seen the generational shift, not only within the engineering ranks, but also within maintenance, reliability, and the technical team. Of a lot of people, again, that are coming in the industry are used to having that information in the fingertips. And I hate to say it about our own industry, but many times we are lagging behind others in having access to that information. So that's been a lot of the driver for many of the digital transformations. Is a lot of it may not even involve you know, machine learning and AI and some of the other elements. Some of it's about just getting all your information in a single platform that you can use. and have access to. So, for instance, be able to get to the equipment data sheets, the last inspection records, process flow diagrams, P&IDs, process data, all of that. There's a lot of different platforms available to you. So oftentimes you can solve a lot of your problems and get some quick gains by just getting all that information in a readily accessible form where everyone realizes that if I go to this location, the information I get is going to be the latest and the greatest and correct. When, again, oftentimes we've been behind in doing that, even simple things like updating data sheets or getting our inspection records properly cataloged and available to people. Sorry, please go ahead.
We got two questions now.
Okay.
One was sent to me by mistake in private, so I asked him to post it in public. You may proceed with the Harry Morse question.
Okay, thank you. So the question was, in your experience, who in the organization is best to manage the digital transformation, a dedicated project team, the IT team? Well, honestly, it's going to depend on your organization. Who's really trying to drive this. I mean, certainly the IT group needs to be involved in it, and oftentimes they have the remit and the space to help bring the team together, apply a lot of the project management techniques that can be important to do. A lot of these were brought from the software industry. And so having IT run with this makes a lot of sense. However, you really need that cross-functional group to make this functional and successful. So as you're identifying, again, we talked about as you brainstorm those ideas of where there's some improvement opportunities available, that's also the time to identify those right skills that need to be part of the team. Again, if you just defer it as an IT initiative, we've seen that those oftentimes are not very successful. And then bringing in those third parties as need be. So obviously there's a lot of providers out there with a lot of great technologies that you can co-create with them. I mean, many of these oftentimes are in their infancy or early adoption ideas. So this is a way to co-create with them and leverage their expertise as well as other parties that can show you how to extract the value and the knowledge out of this. So that's kind of been our experience.
Okay. A question I received from Ricardo, so maybe he did not post this in public chat. He sent that, how do we know that you having good data during the implementation? Are there any quality checks to verify the quality of our data during the implementation?
Right. Yes, there are, and we'll defer to some of the other providers that are out there. But that's one of the nice things is it can look at your data to understand is it of proper quality before you get going. So there's a lot of advanced data science that can be used as part of that. But part of that data review is also just looking at the fundamentals. Again, how often am I sampling particular streams if I need certain property information? Or if you're looking at equipment health, do I have the right temperature, pressure, flow, vibration monitoring, et cetera, locations in order to do this? So it's really going to be a combination of understanding, do you have those right points and right locations, and then that condition checking of the data itself that a lot of these tools can really help with. In the past, we've seen oftentimes in refining and in petrochemical facilities, people have been making decisions on smatterings of data, and oftentimes it's been very experience-based. And that's really the drive of digitalization, is to make it more of a data-driven, data decision-making, and knowledge-based type of an organization, rather than relying on that gut feel and experience to fill in those gaps.
Okay, we have a question from Asrat.
Okay.
From Tabik. He's asking about the basis for eliminating the condition monitoring points. Case study.
Yeah, that's a great question. So in talking to the team that executed it, it was really both of those elements. In some cases, they had locations that they fundamentally didn't need, and they made that decision by applying some of their own standards as well as some of the standards and approaches that we have. But also as part of this, we did find that they had a few gaps, locations that probably needed a little bit more. So it's working through having those standards available within your organization or working with third parties to do those reviews to make sure that you're not increasing risk as part of making that particular adjustment.
Yeah.
Yeah, and I saw Wayne chimed in as well, so I think that's a great point as well to share in that. So for those who maybe aren't seeing in the chat, so Wayne from Aspen shared that in my experience, the best to lead a digital transformation is a dedicated project team, but you need to populate the team with a strong organizational change leader that can help the organizational change along with good technical folks to support. And would absolutely agree with that. Appreciate that. Thank you, Wayne.
Good point indeed. We have a question from Ed Neeler with Norian.
Okay.
Yeah, so he sent the chat, he wanted a comparison from your experience, I think, about applying digital transformation to a refinery versus a chemical process.
Yeah, and they're both applicable. Again, it's really looking about where those improvement areas can come from. As we said on one of our slides, it doesn't have to be the most complex item to implement. And I would also look forward to the other speakers today to share, their review of what they've seen in both of those processes. But, for a lot of this is very driven about understanding equipment health, unit health, and achieving that high reliability. And so, in many of the facilities, whether it's a petrochemical facility or a refinery, they all have pumps, they all have heat exchangers, compressors, piping. I mean, each has different operating conditions and material that flows through it, but a lot of the techniques can be used across the board. It's just on a bit different scale. But I think everyone would agree, in order for us to achieve the profitability targets of our facility, we need our facility to be up and running, reliable, available when we want it, and when we take it down, to do the right maintenance that we need to do and then get it back up. And that's where a lot of the techniques that are out there can help one achieve that, no matter how big or small the facility or how complex or streamlined that it might be.
Great question and great answer indeed. I have a question, Robert.
Sure.
From your experience so far with the digital transformation initiatives, what is the success rate so far? I mean, you see around you, the petrochemical industry.
Yeah, the success rate has not been as good as I think we would all like. I mean, I don't have statistics and percentages on this, but it's a bit of a two-edged sword, so to say, or two sides of the coin. In some cases, it's actually been good to fail, and what I mean by that is, as you're trying some of these new techniques, it's good to find out if this isn't going to work, then let's just stop and let's go to the next initiative. So some of the quote-unquote failures have really been about actually a good outcome, that we find that this doesn't work. Others have been much more successful, and the ones that we've seen that are the most successful, as we alluded to in our presentation, those are the ones that really addressed the fundamental work processes to fix those as part of it, and then took that change management, especially as Wayne highlighted, into account, because this is changing people's jobs, how they function, the work they're doing. I mean, oftentimes you're finding staff are spending huge amount of time just in crunching data. Now, a lot of these techniques are taking that away, and they're having to make decisions off of that data. So do they have the right knowledge and skills and attributes to do that, or does there need to be some training that goes on in order to bring that to bear? One of the pieces of advice I was given, I was in a different forum that we were doing, and we had somebody from a machine learning entity in, and we asked them kind of point blank, is it better to take somebody with a data science background and teach them refining or petrochemical processes, or is it better to take somebody with that process and equipment background and knowledge and teach them data science? And their view was definitely the latter. You really need that fundamental knowledge and information of your particular asset, your processes, your equipment, your failure mechanisms, your reliability, in order to figure out how to do this. That I'm not trying to be unfair to the data science people that are on the call. I mean, they're obviously a critical element. It's going to take all parties. But again, if you want to achieve success, and it's about getting the right people within the group with that expertise and knowledge of all the elements that it's going to take in order to transform.
Okay, thank you, Robert. And thank you, Abu Ali, for joining us. I think Mr. Ahmed Hassani is leaving us. Thanks for joining. Our next speaker is Dr. Paige Mars from Aspen Technology. Dr. Mars has responsibility in enabling digital transformation progress at chemical companies worldwide. She has significant experience with leading operating companies, including Shell, Dow, Sunoco, covering R&D, marketing, commercial, and strategy roles. Dr. Mars will speak about bringing the power of industrial artificial intelligence to petrochemicals. Thank you, Dr. Mars, for accepting our invite, and the floor is yours.
Greetings. Thank you. Very nice to be with all of you today. So today I'm going to talk about specifically more some solutions. You've heard from Robert about some kind of general trends overall. I think what we're going to hear about now is more about individual solutions that you can specifically apply towards petrochemicals. And the key thing, though, when we think about reliability, integrity of assets, artificial intelligence actually brings great capability here, insight on how operations proceed, how to think about reliability and gain some warning about that. And then also, for many of us who use advanced process control, how we can better manage how the assets progress in their operations. And then also we can tune that and ensure that we have good ongoing operations. So I'll talk more about that. And also, I just want to let you know, I think we heard earlier, my colleague Wayne Jergerson is also on. So as questions come up during our discussion, he will be able to address some of that as well as we can handle it at the end. All right, just a quick background. Those of you who are not familiar with Aspen Technology, we are a very well known in the capital intensive industries. Our primary businesses actually are chemicals, energy, and engineering, procurement, and construction. So these are the leading industries, what we would consider capital intensive heavy industries around the world. We've got many customers start in North America, but really the bulk of our business is outside North America now. All the leading companies in the major industries work with Aspen Technology. And the real plus is we've been around 4 decades, so we know this business very well. And as came up in an earlier conversation, understanding the industry is actually really important. And this is an expertise that Aspen Tech has. Many of you may know Aspen Plus. That was our first product and targeted at the chemical industry. And we just continue to build on that capability with additional acquisitions, new product areas that we work on. And I think one of the most important things to think about now also is we build all of this on a platform of data and industrial artificial intelligence. This is really critical. Again, as came up earlier, managing your data is very important. How can you be sure that you've got good data, that in fact you can clean it up as needed, as again, that came up before. But the key is, how do you go the next step and get insight from your data? It's not just, yeah, I've got a whole collection of things. It's, well, where does it help me make better decisions? And that's really the critical part here, is capturing your data and then doing analysis so you can actually make a better business decision, because that ultimately is our goal. Combination of using artificial intelligence, but also the domain expertise, which is so critical. So let's talk about what our challenges are right now in petchem. Certainly lots of major issues. COVID has really changed our world, meant for all of us. One of the biggest challenges, of course, is our work environment is now quite different. So we can be quite dispersed. Some of us are either working at distance offices or maybe even still from home. And how do you ensure that you get good collaboration across your work teams? And then, of course, if you can't be on site, how are you sure that you're able to still maintain a view of what's happening at in your production units? Markets are much more volatile. So how can you work to keep your operations flexible the way you need to, and then ensure that they're always optimized for whatever work environment you may be in? You may not be running at 92% anymore, which is, for most cases, that's what your asset would prefer to do. But instead now, you have to be able to moderate as things change, and maybe as feedstocks are available, because that is an issue with refineries running quite differently than they used to. And certainly we all know that has a big impact on petchem feedstocks. Sustainability, critical topic. Many people are rethinking how they do operations. Certainly you start with looking at energy and water efficiency, but then it's also what new products might I need? How do I rethink things for the circular economy? And all of us are considering the energy transition. Even as a petchem producer, your feedstocks may shift and your energy sources may shift. We all need to be thinking about these things. And then we also are working through the transition of some changing experience in the workplace, bringing in newer people that are very comfortable working with electronic tools, but they also have an expectation about how to work with equipment. They're not going to go out and turn a knob. They expect to be in front of screens. And how do we ensure that all of that works smoothly? These are critical issues that we all need to think about. And artificial intelligence is a critical piece of this. So this is just a recent chart from the World Economic Forum working with McKinsey. And what they're reflecting here is how important AI is. That blue line, the leaders, these are people who invest in artificial intelligence. Yes, it takes some upfront work, but their ability to gain huge value over the next several years greatly exceeds any others of their competitors. You've got people that wait a little longer and think, maybe the technology will get cheaper, or I can do that instead. But in fact, they are way behind in the market. It's really about early adoption, fast movement. And then, of course, those companies that don't invest at all fall way behind and lose market share. And this is a study that was done globally, looking at across industries, but definitely in the AspenTech experience, we find this is true. You really need to use all of the digital tools possible. So let me talk about some of those tools. So I mentioned that industrial artificial intelligence is really critical. So the importance here is it provides you this insight, this ability to think about what you're learning from your assets. So the key is, we know our problems are often quite complex. We have so many variables, so many changing things going on in the production unit. How can we see what is going on and know what adjustments are necessary? We also want to get better accuracy. This is back to the data cleanup stage, which is very important. And that's critical to understand the operating environment that you're in, to know how to work through all that data. Also want to give some guidance to users. So this is back to when we're thinking about new users we may be bringing in. People are younger who haven't been at the unit for 20 years. How do you give them some guidance about how to do operations? And we also want to automate some simple processes appropriate to do that. Initially, we're starting automation with kind of simple aspects, and then later we will be moving to trying to towards the self-optimizing plant, where you can think about much less interference and really where we have to engage only when things are way out of range. And then overall, what this does too is it reduces the total cost of ownership, because the assets are always running smoothly and we're comfortable with how things progress, and we can predict what the unit will actually do. These are critical aspects for future work. So if we look at the key things, when we think about what you need to run the unit, and thinking about heading towards the self-optimizing plant, where it can run itself with less engagement, with less involvement from the operators, what are the key pieces that you think about? So initially, obviously, in the center box here, production optimization. How do we assure that we optimize production as much as possible? And then pieces that contribute towards that, of course, are on the right: reliability and maintenance. So how do we best think about what's the condition of the plant and how we can work on that? And then, of course, performance engineering on the left. Fundamentally, what do we design into the unit or adjust in the unit if it's an existing asset to make sure that it can produce most effectively for us. And then also this is where digital twin comes in as well, where you can use simulations to help improve your overall operations. And running throughout it all is value chain optimization, where you think about how do you get your feedstocks in and then your products to customers. So we think about it in terms of this total picture that thinks about all these components in operations. Okay, so let's talk about a specific solution. One of the critical areas is for maintenance, of course. So when we think about asset reliability, the concept of prescriptive maintenance is very valuable. And the idea here is that you gain warning about a potential problem in operations, and then it gives you an idea about how to address it specifically. And this is a big concern, of course, in terms of reliable operations. So the key is, if this is using artificial intelligence, specifically machine learning, where looking at past data, you recognize patterns that predict degradation and future failure. And what's very important here is there's excellent accuracy in this particular product from AspenTech. So we know very well that the predictions are something that's real and in fact is reflected in the operations of our customers. And the key is you get significant warning. And so you can plan for weeks, sometimes months in advance about whether or not there'll be a failure. And you can think about then, how do I best prepare for that? So of course, with that, the first thing is that you avoid a potential safety situation, because often a failure can be quite a surprising event. But then also there's can be an environmental impact, and then an unexpected failure can also be much more expensive. So these are the important things to consider about getting advanced warning about potential failures. And here's an example: ethylene furnace. I think probably many of you operate these. Getting advanced warning about problems for fouling in a furnace. This is a very common issue, of course. And so if we can get a few days warning, we can then plan better for it. And in fact, and also take it down when we need to. Not a lot of people just do kind of routine clean outs of ethylene furnaces, but what if you knew better when it would actually fail, and then could maybe go a little longer? Of course, we all know it's feedstock and operator dependent in terms of the operations. So if you had a better sense of what was going to happen, you could plan for your maintenance differently. And the key is, overall, you'll have less downtime if you can plan for this. Energy savings, and you're running better. You don't have so much issue of large energy consumption when the furnaces are not running well. And then overall, you can extend the lifetime of the furnace. And then you're also increasing knowledge about the operations. And so this is a critical area. And for this particular European petrochemical producer, they were able to avoid 1.7 million euros of losses. So a significant value to them. Another example too in petrochemicals is, this was in a low density polyethylene unit. So if you're familiar with low density, it's a high pressure process. And hypercompressors are particularly important in this process. And again, doing a survey of the data that this European producer had, they were able to gain 27 days of advance warning of the failure of this hypercompressor. And again, you know in advance, now you can plan for it. You can take it down in advance of the expected failure. You're sure that you avoid a potential safety situation, maybe avoiding extra flaring that can also occur. And then also importantly, you can build the right inventory before the event. All very critical when you think about making sure that you're able to meet your customers' needs. So this advanced warning helps immensely overall with the process. So now let's think about integrity. So that was mostly a reliability focus, but what about integrity overall? So if we think about it in terms of design specifically, how can we get a better sense about what our units can actually produce? Simulation is very useful here. I'm sure a lot of you have used it in your engineering work to simulate the process and then make better decisions, first about how to maybe build the unit or revise the process, but also how to optimize. You can use that digital twin to optimize. So overall simulations are really important. But one thing though is they don't always work perfectly. So just introduced a new capability called hybrid modeling. I don't know if you've heard this term before, but it's the idea here that we're blending capabilities to get the best possible out of the simulation. So I think we know that first principles models can't solve all the problems. And so sometimes what you have is requires significant expertise, and sometimes you've created such a difficult problem, it doesn't even converge. So that can be an issue, particularly if you've got a unique situation in a particular process unit. And then on the pure machine learning side, though, is that you can build a model based on data. Now, this is back to you got to be sure you've got good data. And also, you may find, though, that sometimes operating data doesn't really extrapolate well. It doesn't fully represent what's going on. And also, it can be difficult to interpret. It's really without bounds, and you need to put bounds on it. So what we've now introduced is the ability to combine both of these concepts. So you're taking everything you basically understand about the chemistry in the first principle and engineering in the first principles model, and now combine it with data, machine learning, artificial intelligence data, to get a better simulation, something that's more useful to you, and also that you can prepare much more quickly. And this has got great value then when you want to apply it towards operations. So just an example here to kind of talk through it. So what does it deliver for you? The key is flexibility. You can now simulate more processes. I think came up earlier about what about kind of a small petchem process, maybe not as big as a refinery. Well, if you can apply the simulation capability to maybe a more unique process, you can still get the insight you need there without huge investment. And so we'll be able to apply these capabilities to many more operations, many more processes. But then also it can help us with our most difficult problems, because it's this combination of first principles plus data. Those together gave you really insight. Another plus is that you don't have to be someone with 20 years experience of running Aspen Plus or HYSYS. You can provide some guidance, in context guidance to newer engineers so they're more quickly able to use the simulation capabilities. And also, it doesn't require you to be a data scientist. It's this unique combination of blending both worlds and overall making it easier to work with. And then you end up with models that are valid for a longer period of time. I think if we've all dealt with models of different parts of our process, it's a big issue sometimes when the units, they no longer reflect what's actually going on, and now you can make adjustments and it's much more easy to work with. So some examples of this is recently a major Asia Pacific company was able to use hybrid models to help in transition time in polymers. And those of you who may be involved in the polymers area, you know, often you have a lot of different products that you make on a single line, and you effectively waste both feedstock and reactor time in this period in between when it's not on spec. So if you can reduce that transition time, so you have less waste between polymer grades, that's a huge value. It's about reactor availability, which is worth a lot of money, but then also you're making less waste. And as we brought up before, all companies are concerned about being effective with operations such that they make less waste, and then you're not losing raw material into a product that you'd rather not make. So the key is insight from the hybrid models was able to better predict how the quality of the polymer such that you could narrow the amount of material that's made in between the preferred grades. Overall, this company was able to cut transition time by 50%, which is a huge savings, at least $700,000 a year. This is early estimates, in fact, because they're beginning to apply to more and more application areas, and helping the company also achieve its sustainability goals, which is about reducing waste throughout its processes. Also, one thing I think important to think about too with any type of simulation, but particularly with hybrid modeling, is how can we use this capability to address some of the critical challenges of the circular economy. Those of you who may started to work in this area, pyrolysis is an area of interest where you can take a mixed plastic stream and then convert it in either to a raw material that can be used for other petrochemicals or maybe back to the base monomer, often referred to as chemical or molecular recycling. Using a simulation, it will help you better design the process to do this. We have many customers all over the world right now that are looking very closely at this problem. I think we all understand the challenge of plastic waste around the world, and our ability to address that problem is something that all companies want to get involved in right now. So this is an important new solution to help resolve some of the challenges for the circular economy. Also, using simulation is really important to help you think about energy efficiency. You can look across your site, first optimize for heat integration. That's a critical issue, right? Think about where you can share heat with different units. Energy recovery throughout the entire system. And then also you can look at individual pieces of equipment. Sometimes it's a heat exchanger that's not working well, so you can look at that as well. And overall, look at your site and think about your carbon footprint and how you can reduce energy uses. This capability also gives you the ability to look at other utility sourcing capabilities as well. Maybe you want your energy sources to be lower carbon and you have access to solar panels or windmill, and you want to be able to integrate that as well. These planning tools help you do that better so you can really address the carbon footprint of your assets. Again, critical future needs for companies now as they set significant sustainability targets. Here's just an example with Latte, where they took several Aspen solutions to look at overall the very large complex. How can they address energy reduction? And they actually had a specific CO2 reduction target that they were working on. And they were able to come up with several different ideas, and now they're gradually implementing them. Thus far, it's achieved 17% energy reduction, significant energy savings, but they continue actually to implement these projects. They have a huge list that they were implementing over a few years. So looking at how we can be more efficient with energy across our assets is a very important future activity. So let's talk about integrity in operations. So now we're in the central box. We've talked about reliability, we've talked about engineering, but now let's look at the fundamental in operations. So I think most of you probably are working with advanced process control in some way. Most petrochemical units now have APC on them in some form. Not all those, so maybe not all of you are working with APC. But the key is what advanced process control does is it lets you make tiny changes so you are sure that you are running your assets as smoothly as possible. You let the computer take over, run the unit, as they say, make these incremental changes to ensure that you're always running in the optimal box. Optimal for production, optimal for energy consumption. Now we can apply artificial intelligence here, so we learn from previous operations, and it gives us even greater insight as to how we can operate. Lots of challenges in petchems that we need to think about where AI can be really helpful. One of the key areas, of course, is nonlinear processes, and I'm sure many of you deal with those. So many of the petrochemical polymer processes are nonlinear. So you need this insight from previous operations to be able to address that. So this is where AI can really help. One way to describe it is a familiar chart here for how you think about APC. What we're looking at is profitability on one axis across time. And so when you think about when you turn on an APC unit and you begin to optimize and you get to a preferred position, but then what you find is that you get some degradation over time. It could be a variety of reasons. You could have fouling building up in your system. Maybe your catalyst does not work as well as it once did. They always have a catalyst lifetime to consider. Maybe you've made some changes to your process after a turnaround. But what you find overall is you get degradation in APC. And in the end, this results in a significant red area here of lost profit. You're no longer running at the optimal state. And so you need to go back and retune all of your APC. And this can take significant effort. Now, if you apply artificial intelligence here, you don't have this degradation. You're able to stay at high quality because you're using AI to give feedback to the system so it re-optimizes all the time, helps you regain this benefit. Significant value here. And one way to think about it, this is kind of the traditional approach, is that you take your data and then you kind of cut it into pieces and you look at specific cases, and you end up spending a few weeks trying to retune your APC. You use industrial AI now, where you're taking your data already from your unit and you apply that. You now can do the retuning in a matter of hours instead of weeks. This is a huge change for operators now, that you can apply this capability so you're much more efficient than in your APC. And again, you've got capability that comes from the software, so it doesn't rely on the depth of experience of staff, and instead now it allows more people to be able to help with the APC tuning process. And again, lower cost of use overall, because it makes you more efficient overall. One key thing too is it also helps you expand the benefits of APC. So maybe you've got a few units that may not have APC, or certainly not a well-tuned APC. Now you can use the data you've been collecting to improve that APC, or build the first one that you have on a particular new unit. We're finding lots of interest, particularly in the specialty chemicals area, where companies have decided, too small a production, I'm not going to use APC. But now with much faster implementation, many more processes can be available, so you can gain the huge productivity and cost boost by using advanced process control. So, in conclusion, the key with all of the solutions that AspenTech delivers is that we really want to help you run your assets safer, greener, longer, and faster. I think a critical consideration is, as we look at all of these metrics around here, digital really helps you achieve the performance that you need and chart your progress. You can now look at your emissions across your asset. You can understand reliability and predict it and improve it. And then overall, of course, margins is always our critical component, and all the while ensuring that we maintain safe assets. Always important for all operations. So thank you for your time, and certainly I think we've got maybe a few minutes for questions. Wayne can also help with that as well, so thank you.
Thank you, Paige, for a great presentation. We appreciate your time for preparing the presentation. Thank you. We got some questions, and Wayne Jurgensen from Aspen addressed some of these questions already, and he said he will be answering these questions, some remaining questions. So, Byron, could you please unmute Wayne? Wayne,
I believe I'm unmuted now. Can everybody hear me?
Yes, we do hear you. Please go ahead and answer the questions. Thanks for taking the initiative.
Sure thing. So the first question I did answer in the chat was about failure modes for hypercompressors that machine learning has been able to find and do. And the answer to the question is the main failures are not only just valve failures, but those are typically the main failure mechanisms. And it's not that the valves fail that often as much as they just get dirty with polymer. That's a very common thing with hypercompressors. So in essence, they fail because they get plugged up. So that's one of the main failure mechanisms. And then, of course, cylinder failures are commonplace, and packing leaks. Bearing failures can also be predicted, but with hypercompressors, they don't actually happen very often, at least in my experience. Bearing lubrication issues, they do occur, but and the machine learning will find those, but they don't actually happen very often. And then the follow-up to that question was the follow-up was what data do you use within machine learning? Is it inspection data, or manual entry data, or is it real-time data? The answer is it's real-time data. So typically you're using the most common data source for machine learning is your historian. And that's where most of the data comes from. And you do have vibration protection systems, and you can plug both of those into the machine learning algorithms. Normally, from a data handling perspective, you take the vibration and the machinery protection system data and put it into your historian. And then that way you're only pulling from one data source, but you can pull from multiple data sources if you need to. And then you need the timestamps to mark when the events occurred. So if you had a cylinder failure 2 years ago, you want to know when that occurred. So then that way you can point the machine learning algorithms to those points in time for it to learn that failure mechanism to predict it for the future. Okay, so that was around that. And Byron asked a question. For AI to be successful, how much data is required to be collected for the AI to make correct analysis? Is it years, months, or months? Is it a specific data source that is collected from, or multiple data points? So I already answered the multiple data, the data sources. It's typically your historian. And for most problems, you typically use a year's worth of data, just 1 year worth of data. You can use machine learning on new equipment with as little as 2 months of data, but then the machine learning will learn as it goes. So the models actually get better over time when you feed it more data, but you can start with as little as 2 months worth of data. Now, there are some problems in the hybrid modeling world that you will want multiple years worth of data, but it's going to depend on the type of problem. You know, for a typical rotating piece of equipment, you really only need a year's worth of data, but for more advanced problems that occur over very long periods of time, you might need a couple of years worth of data. And then Salam Al-Adba asked the question, what level of system monitoring infrastructure is required to run AI machine learning in assets? For assets, for sure, assets are not all the same, and the solutions won't be to live with whatever the asset has. So not exactly sure I understand that whole question, but the monitoring infrastructure is typically, you can set it up in the cloud to connect to your historian and run in the cloud if you want to do it that way. Or you can install it on a private cloud for your companies or on private servers within your company's infrastructure. There's 3 different ways. I found that most customers like to put it on their private infrastructure with a couple of servers in there for data and cybersecurity reasons. And that's perfectly acceptable. And, you know, but any one of those 3 methods will also work. Okay. Another question, and I believe I'll throw this one to Paige. Hopefully she can answer this question. It's whether Aspen have APC implemented in power generation plants. Have we implemented APC in power generation, as well as the carbon capture storage process with AI data-driven models? I am not sure of the answer to that question. Paige, do you know? I'm going to answer another question. It says,
Go ahead.
Aspen implemented any online degradation monitoring online tools for stationary equipment and pipelines to get real-time data? The answer is yes. The typical stationary equipment problems are, lots of them are on heat exchangers, which would be fouling of heat exchangers, and doing a good prediction on that. And then Paige actually presented one case study on furnaces, predicting the coking cycles for ethylene furnaces. And then on pipelines, we have recently built some AI models for corrosion monitoring on pipelines. Now, however, this is in the infancy stage, so it's not very well developed yet. So I will say that, and it does require that there are corrosion monitoring being readings taken on the pipeline over a very long period of time. Pipelines degrade, over very, very long periods of time, 5, 10, 15 years. So you do need that corrosion data for very long periods of time for the system to work correctly.
This is Paige. I'm sorry. I actually, my system crashed. I had to exit the system and come back. So that's why the muting problem. Yeah, we do have a few examples in Power. Not a lot though, but we do. So if you want to send me your details, you can send it privately and I can share those with you.
Okay, thank you, Paige. Thank you. I think we don't have time for further questions now, but please, you have the contact information of Wayne and Paige. If you have further questions, you may contact them, and you may also contact them using the chat to get their contact information. Our next speaker will be Mr. Yusuf Mohammed from VTech Coda. Mr. Mohammed will be speaking about required capabilities to achieve digital transformation. Mr. Yusuf is having 33 years of experience in industry, including IT services, digital product engineering with digital transformation and cybersecurity. He has led digital transformation, security, and digital engineering practices with several responsibilities. Thank you, Yusuf, for accepting the invite, and please proceed. The floor is yours.
Thank you. Good evening and good morning. Assalamu alaikum to all of you. First of all, thank you for giving this opportunity, and it's great to connect with all of you. I think in the first two sessions, we heard about the digital transformation and a specific case from the prescriptive maintenance and the AML technologies and so on and so forth. In my presentation, what I'm going to do is I'm going to talk about some of the required capabilities, to achieve successfully the digital transformation, and what kind of methodologies and other things, that we need to follow. Okay. In terms of just to recap here, I just want to reiterate that digital transformation is all about user-centric or user-focused, and it is a business transformation. Okay, and technology is just a function as they enable. Okay, so most people think that just making a mobile app is a digital transformation. Its technology is not the digital transformation. It's more of a business transformation impacting the end user and the customer. Okay, so that's a key part of it. And who we are? I'm Yusuf Mohammed. I'm part of VTech Coda. And V-Line is, all of you know, V-Line is the leader in the business of providing MRO services in Saudi Arabia as well as the rest of the world. And Coda Technology Solution, based out of India, is primarily focusing on data services in MRO and also giving transformation of business through their IT and digital solutions. And both the companies come together and created VTech Coda, an amalgamated organization, primarily focusing on the petrochemical oil and gas industry, on data services, digital transformation services, and IT services. Okay, specifically on the MRO side as well. So with that introduction, so I will quickly cover what are the what is the main impetus of the digital disruption, and what are the capabilities, steps needed for going to do a digital transformation, going for a digital transformation journey in a successful way, And I will also take some illustration in an MRO area in a very brief manner, because that's not the intent, because we have already heard and we are also going to hear in the subsequent presentation. And then I'll also talk about how do we build those capabilities, in terms of building in-house and acquiring and outsourcing and insourcing and all the aspects. And finally conclude with the key success criteria. Okay, and before we jump in, I just want to give this digital disruption S-curve. All of you know that S-curve on various technologies and other areas. And in the digital side, what McKinsey has published, some time back, they put the disruption, initially, it comes as a deductible form and with the faint signals, and then it becomes a validated model in a clear signal, and then eventually, it becomes like an inevitable critical mass adoption, and finally, it becomes a new normal. You can always relate this with a cloud technology. 10 years before, it was just deductible and slowly moved into clear. And today, it is sort of inevitable, and slowly it will get into a new normal. And the same as software as a service as well. Okay, and the same way, if somebody is doing the business, the incumbent, and it is really, really important to understand this disruption in place, because in the current context, no industry is immune to disruption caused by this the business model. Okay, so and the people who take the bold transformation strategies will become the winner for future, and they use the combination of both offensive and defensive strategies. Okay, the others will be just following followers, and they will slowly get successful in their business, or they will fade into the history, in the later part of it. So it is very, very important to understand this disruption, take action at the earliest. Okay. And so when we talk about the digital transformation, you also need to understand what it means. People think that the difference is that people thinking they have a digital enterprise is different from digital enterprise thinking. Okay, so some people they use the digital just to create a better version of the past. More in terms of focusing on the efficiency is very different from using digital transformation to create a new feature. This is what we want to talk a lot more about. Creating a new business model, new future. Which is where the impact of digital transformation is a lot more effective than just focusing on the efficiency or creating a better version of the past in the better version of the past. Okay, and so in order to embrace this digital transformation, why we need that? Obviously, it is from the customer experience standpoint, and that is the key part of it. And giving the omni-channel experience or agile and responsive, we already heard in the earlier presentation. The second one is creating a better future through the efficiency by improving the bottom line, and automation and orchestration is going to play a key role along with the cloud. And this is the important thing, recession-proof business, the innovation for new products and services. Now, how do we use the digital transformation in terms of creating a new revenues, new business model? That is the very effective outcome that we can see through the digital transformation process. Okay, so in order to embrace this digital transformation fully, because in the earlier one of the questions is that what is the success rate of digital transformation in an overall sense? People say that 70%, around 70% of the digital transformation projects don't succeed, mainly because they either exceed timeline, or the poor return on investment, or the rift between the business and IT. Okay, there's not much collaboration, not much change management that has happened in the organization. All those things has made some of the digital transformation not successful in the thing. But in order to make this successful transformation in an organization, it is very, very important to use this in a structured way, in a structured framework, so that we understand the steps, we understand the process, in terms of how to do this transformation and eventually get the benefit. Okay, and it is similar to in the ITIL format, when in the process and in the or infrastructure industry, the ITIL is a known framework and methodology. And similar to that, we should have some sort of a framework and methodology to implement the digital transformation so that we become successful. So towards that, I want to talk about some of the 6 steps process in terms of, how do we enable the business transformation? And there are 6 steps. The first one is the digital capabilities assessment. As an organization, as an industry, as an organization, as a company, what are the capabilities that we have, and what level of the intensity of that capability that we have, assessment. And then the second step is identifying the right digital use cases, digital use case mapping, so that we attack the right problem in terms of solving the problem and should be able to get the benefit. And third is obviously the benefit analysis. It's not about just identifying the use cases, but you also need to understand, what it takes to implement that use case and what is the benefit that we get. And then if you have multiple of those use cases, and what is the business priority assessment? How do we prioritize? It's not a one time. It's going to be a journey as sort of doing the business transformation. So what is the business priority? Priority assessment, and create the roadmap, for implementation, and finally creating the business case development. These are the steps. Some similar to what we have seen in IT process, but if you go in a structured way, and it is very, very, easy, to attack the right problem and able to get the benefit. The step 1 is the digital capabilities. So I want to talk about those the building blocks of 6 capabilities that are very, very important, to enable the digital transformation. The innovation capability, transformation capability, and IT excellence. Those are all the 3 things that I have shown left. And then the customer centricity and the effective knowledge work and the operational excellence on the right. These are all together, is 6 capabilities that we need to understand what we have and how much we have. And if you see that, this innovation, transformation, and IT excellence are sort of an enabler to get the end results or the goals in terms of the customer excellence, effective the team and the organization, and getting the operational excellence. Okay, so this is a enabler, this is the goal. Together these 6 elements define the digital capabilities. And from the enterprise standpoint, we really need to understand where our capabilities are. Probably we can use the spider chart or the radar chart, the way I have shown, in terms of the heat map, where we are in terms of those all 6 capabilities, right from innovation and to transformation to the customer centricity, operational excellence, and other things. So this is the first step, which gives you what kind of capability you have, whether you have any of those things or all of those things, at what level you have. So once we do this capability assessment, the next thing is the digital use case mapping. So what are the different use cases? What are the different problems that we want to attack? And if it is a new future that we want to create, what could be the model? What could be the new innovation? Or what could be the new thing that probably we want to create? So define those digital use cases is very, very important. Give the description, what is the current situation, if it is you want to solve some of the existing problem, and if you solve that problem, what is the value proposition, benefit, and obviously do the risk analysis. And these use cases can fall into any of those the 6 capabilities that I talked about. And in order to create an impactful end result, probably set of use cases can fall into any of those capabilities. Okay, so that's the key part of it. And the use case is very important. When you identify the use case, it is important to understand what problem it is going to solve. It is relating to the business problem. And it's also very important to create a collaborative environment between IT and business, and getting all the stakeholders in place, so that as a effort, we are creating these use cases. And the third is the understanding the benefit. Okay, and after creating the use cases, we need to know for each and every use case that can fall into any of those capability metrics. So what is the benefit that we are going to get? I just want to show this in a 2x2 graph. On the x-axis, importance to the current business and the y-axis, it is important to the future business. Okay, so if I create cases which are equally important or high importance both for existing and the future business, that is going to be the very strategic. I mean, that's where it gets high attention in terms of the invest perspective. And if you want to solve some of the existing problem, and it's going to be very important for the current business for improving the efficiency or the bottom line and other things, it becomes operational. It's also important to ensure that we invest and solve that so that we sustain and then and able to grow the business. And if something, use case, if you find that it's neither important for current or the future business, obviously, it's something we have to just divest and give the support and probably come out of it as quickly as possible. The last one is may not be important for current business, but if it is very important for the future business, this is where you have a potential in terms of seeing. Whether if I do some investment, whether I should be able to get the benefit, what is the timeline involved, what are the risks involved. But this is one area where you have a potential use cases. Probably we need to treat it separately. Okay, so this 2x2 graph will help you, to map your use cases based on the benefit. And the next step is the priority assessment. You might have multiple of those business cases, and it is very difficult to implement everything all together, time and resource and all those things. So you need to prioritize those business cases. And again, we can use a 2x2 chart. What is the easiness of implementation in terms of the resource and timeline, and versus what is the benefit that I get. Obviously, the quick wins are easy to implement, and I get the business benefit much higher. That is something we have to quickly identify and implement it, because it is a win-win both from the easiness as well as the benefit standpoint. The other one is easy to implement, but the benefit is not that much, but some benefits are there. To me, I think it's a low-hanging fruit, and as and when you have the resources and time, probably you should attack that, so that you should be able to quickly implement and be able to get the benefit. Okay, and something which you don't want to touch is very difficult to implement, and you don't get the business benefit. That's something we don't want to focus on. And the last one is you get a good higher business benefit, but very difficult to implement, or it takes time, or it needs a lot more energy or the investment. This is where strategically you need to focus. Hey, I'm going to get more benefit, but is there an opportunity, various options available to do this implementation? Is there a way to able to schedule it and able to mobilize the resource to do that? And definitely it is a must-have, but it needs a lot more attention and planning for implementing those things. So this step, step 4, business priority assessment, really helps, coupled with the business benefit analysis, so that we have set of use cases, we know what benefit we are going to get, and what is the priority that probably we want to do that. So once we are done with that is where we need to create a roadmap. Okay, so you will have set of use cases. Probably it is not one time. We need to create a roadmap of it. It can flow for multiple of years, and which are all the use cases. You club some of those use cases so that you can create a meaningful impact in any of those capability areas, whether it's a customer specific area, or the excellence, operational excellence, IT excellence area, or the digital, the effective knowledge working, or the innovation area. Okay, so identifying those use cases, prioritizing and creating the roadmap is very, very important. So once we are done with this roadmap, and then we should create a business case development. Talking about what is the need for it, what is the problem statement, and what is the project options available, schedule, and impact. Obviously, do the risk analysis. More importantly, doing the financial analysis with the cost and return of an investment, and that gives you a very good business case or business plan, to get a proper approval to go for it. Okay, so this is a 6-step process. It may look obvious, but very important, to make the digital transformation journey to be successful, and approach it in a methodical way. So once we are done with that, obviously, we need to do the business transformation management principles, like the strategic management and the value management, and the risk management on one side, and then you also have the program and project management side, and the business process management, and the learning and the training management, and the risk management and other things. Okay, so the general management principles are also equally important apart from these 6 steps. So with these principles, I mean, this is very important, and in order to be successful, and I just want to highlight those elements so that all of us are aware of this. So with that, now I want to take some illustration, some of the problems that we have identified, we want to solve, or we are in the process of solving using our partners, along with our partners. Okay, so I want to take some one illustration quickly, and being in a MRO and the data services side in VTech Coda. So we took some of the challenges in MRO, and obviously all of us know that in MRO perspective, it is an increased product complexity and the number of variants, and the human error cost about 80 to 90% of all industrial failures or mishappenings. Equipment failure due to improper maintenance is the cause of 42% of the unplanned downtime. Okay, so this, I mean, we also heard in our presentation as well. And so this is an important aspect. And how do we solve this problem? There are 2 ways of looking this problem. This gives a typical MRO process and pain point. Now, once the damage happened, there is an analysis, and then try to get the part or the equipment and do the disassembly and do the MRO and assembly and QA. I mean, this is a typical process that we follow. Our objective, I mean, in terms of goal is how do I avoid the failure, okay, or damage incident. Okay, assuming that it has happened, I mean, what is the quickest way of solving that? How to reduce throughput time? There are various TTPs, throughput time that I have mentioned in the chart. I mean, how do we reduce those times so that I should be able to get my equipment or part or whatever, and so that the overall throughput time is very optimal or lesser. Okay, so these are all the 2 major objectives and in the MRO. Towards that, okay, so I just want to introduce the data services from VTech. We deal with the master data, maintenance data, and the warehouse data on various aspects, and we want to solve this using our knowledge or the domain knowledge from the data perspective. Okay, and we heard about AML in the earlier case, and the domain knowledge is important from the data on one side, and using those digital technologies, which is the available technologies like IoTs, blockchain, artificial intelligence, and machine learning, and AR and VR, virtual reality and augmented reality. Okay, these are all some of the digital technologies, and the data is going to be the major player in solving this issue. So together, I mean, and using the reliability principles, and I think we heard some of those things in the earlier presentation. How do we use some of the digital reliability data like live data analysis and the failure mode and effect analysis? I mean, and in terms of identifying the risk, and so that potentially, we can mitigate the potential failure mode and associated costs. So with that, we also want to talk about the digital twin. We already heard about that, and you can create a digital twin for an equipment or for a plant, or a unit, or the whole factory. And in this particular case, we created a digital twin specific equipment which was seeing a lot of failures. And when I say digital twin, the modeling data, the geometrical data, as well as the transactional data, in terms of the price and the vendor and so on and so forth, all put together, is going to help me to do effective analytics, using the machine learning technologies, so that we should be able to solve this problem. So here the problem statement is, I mean, how do I reduce the throughput time, or if possible, eliminate the avoidable failure? I mean, that is why I need this this solution. So how do I do that? I use the reliability data, and how I do that using the AML technology. So we did one of the projects with our partners, and for a specific manufacturing industry in India, where we use the process data using the IoT sensors, and predicted the health of the pump in this case, and using the big data analytics. And more importantly, we also analyzed the purchase analytics. We did that in terms of who is the right vendor, and who gives the better price and the better quality and all those things, so that even if I need to procure, I should be able to do it in a much faster, much better price. And so in this case, the impact that we created is, earlier it was about 30 weeks, right from the time from the failure to the part replacement, and we were able to reduce 4 weeks together, in terms of predicting the failure in advance, or to some extent, predicting the healthiness of the equipment, and also optimize the whole purchase process. This is one example. The second one, a very interesting thing that we are working with one of our partners is using the AR, VR, and MR technology. All of us know that virtual reality has been there for quite some time, especially in the flight simulation side. And how do we use those, leverage those technology for augmented reality or mixed reality, in terms of the real-time scenario in the real environment, so that we should be able to bring a very meaningful impact from the services standpoint, either for the service training or during the service, in terms of the assistance or serviceability validation. So, and today, if you see that the whole AR hardware is also sort of maturing, or sort of matured, and we have various hardwares available, right from Google Glass to Microsoft HoloLens, and Vuzix, and the smart glasses, and so on and so forth. With that, and so we should be able to do the service assistance using augmented reality. For example, in this particular case, a person is doing the service. He's been equipped with the tablet or the iPad. Through which you get sense. And he is also able to connect lively, with the support engineer who may be far away, from the plant. Okay, so that the communication is there, and the augmented reality gives, if there's a specific failure, what are the steps he needs to take? The service assistance. In one example, in this particular case, how we can use mixed reality or augmented reality, to effectively do the service part of it. And the same thing for service training as well. Here we will use a virtual reality created.
Mr. Mohammed, we have only 1 minute to conclude, please.
Okay. So from the training standpoint, we can create the simulator in terms of doing the service training. So the last part of my presentation is, in order to build this capability, traditionally, we build the capabilities in house, or we take help from the partners, or doing the outsourcing. So in the case of digital, it is a lot more different than traditional outsourcing. The traditional outsourcing, we go with the system integrators and the long-term kind of contract. But here, the niche players are playing a key dominant role, because they are bringing the very niche solution, in terms of implementing the digital, and more importantly, the change management is very, very important in the organization to bring those changes, so that we should be able to build the capabilities in-house, and also able to use the niche players, who are having the niche solutions in the digital technologies. With that, this is my concluding slide. For the success criteria for digital transformation, obviously, this is my leveraging the structured methodology is key part of it. Focus on change. Culture is important. People, process, technology is very important. And consumer and user centric is very important, in order to get the better impact. And the sourcing strategy, or the building the capability strategy, is also important, in terms of using the right structured methodology. So with that, I'll stop at this point, and thanks for giving this opportunity.
Thank you, Yusuf, for delivering the presentation. Very informative presentation. Thanks for your time. We had one question from Mr. Murphy. He's asking about the baselining of the performance, and this is becoming a challenge. So how to overcome this?
Yeah. So the baselining the performance, for example, no, it's very generic term that you are asking, so what probably we need to do is once we identify the use cases based on the capability that I talked about, and if you want to get the better future, no, by implementing these digital technologies, so we need to understand what is the baseline performance. I mean, if you talk about the baseline performance in terms of the example I gave you, no, in terms of the purchase, in terms of giving the order to getting the part. Now today, typically, it takes X number of weeks, kind of thing. Okay, and is there an opportunity to reduce the timeline 50%? Okay, so anything and ever that we want to create an impact, create an efficiency, first to measure what is the current baseline, no? Whether it is the purchase data or whether it is the performance data, whether you want to improve the performance, for example, in the chemical industry. So measure the current performance and give, I mean, if there is an opportunity to improvise, what is the goal that we have to set it up? So that is how, the measuring the current performance is important for identifying after identifying the right use cases, so that we should be able to create a how part of the journey, to implement the digital transformation.
Clear. Thank you. Thank you very much, Mr. Yusuf. If you have any questions, please forward them directly to Mr. Yusuf. He shared his contacts in the last slide. Please feel free to forward your questions to him. Next presentation would be about equipment predictive analytics. So as explained earlier, we will take, this roundtable and the presentations in blocks. We'll start from the definition of digitalization. How can we enable digitalization? Then now we'll speak about analytics. Then we'll speak about digital twin and some applications. So we will take this smooth flow, and hopefully this approach will enable us all to get a better understanding of the digitalization in the petrochemical industry. Our next speaker is Mr. Fida Khalil from Siemens. Mr. Khalil is a team lead of digital transformation. His responsibilities include delivering artificial intelligence solutions for process industry customers in the region of the Middle East. Fida has 14 years of experience in power generation and process industry, working in leading positions, including customer service and R&D. Mr. Fida, thank you for joining us, and the floor is yours.
Yes, hello everybody. Can you hear me?
Yes, we do.
Okay, perfect. Thank you very much. So first of all, it's a pleasure for me to be invited to this forum and be able to present our predictive analytics solution from Siemens. Basically, with me in the call is Monika Höldinger. She's the head of the predictive analytics from our global headquarters in Germany. Maybe before we start, some information from Siemens as our company. As you may know, Siemens is a global technology provider where, amongst others, we are focusing on industrial automation, and now a very big pillar is also digitalization. And I think we heard already a lot of great content also from other companies. And also we as Siemens see this as the digital transformation as one of the main pillars, let's say, throughout also the next years in the industry. In a very close cooperation with our partners and customers, we are driving this digital transformation and also in the process industries such as petrochemicals. So just to know that we as Siemens, we are investing also significantly in research and development and software, and also certain software acquisitions to refine and also improve our digitalization portfolio. So basically, just to give you an idea, Siemens, I think over last years is investing approximately annually over 5 billion euros in research and development, and we are having over 40,000 employees working in the research and development area. Focusing on petrochemicals, we are based in the digital industries and developing and having solutions exactly for this industrial market. So, and here exactly comes our Siemens Predictive Analytics solution into the place, which I would like to explain to you today and show up one case study. So, yeah, what is important nowadays? Talking about digitalization, again, we heard already a lot. One main important topic definitely is, I think, throughout the different areas, is to protect the business, to have a secure business. How does unprotected business look like? We do have people and assets which are exposed to risks. We have business which is vulnerable, let's say, to disruption, sabotage, and even theft. We have, of course, a lot of costs and which are also then connected with this, and maybe also reputational damages which can happen also, let's say, throughout the different stages. So that's why we also see that one of the most important targets for this digitalization is creating a secure business. And secure here refers to creating a safer and more resilient environment and production plants, more sustainable business with the possibility or to be able to resume the operations faster, to increase operational efficiency, and which at the end of the day also ends up in gaining the trust with our customers and shareholders. So I think we heard a lot about data and it's important. So now let's talk about the existing data. The existing data is the starting point for digitalization. Only by using the data smartly, you will be able to manage to increase sustainability and energy efficiency, to assure the security and the business continuity, to demonstrate compliance and productivity of people. We will focus today on showing how to maximize the asset utilization and improve operations and OEE by using the plant data intelligently. Having mentioned the overall equipment effectiveness, we touch here also a couple of topics like production efficiency, plant availability, and product quality. All these, along with the asset utilization, can be directly improved by using, for example, the power of artificial intelligence, and this was also already mentioned in one of the previous presentations, where we definitely confirm also the domain knowledge for the different industries. So somehow we will need to combine exactly topics like machine learning, artificial intelligence with the domain knowledge in order to tackle exactly all of these points. And for this, we from Siemens, we have developed a solution called Siemens Predictive Analytics to exactly tackle this. So how does it really work? So when talking about artificial intelligence, we need to do some engineering by integrating and taking into consideration multiple different data sources. We're talking about DCS systems, historians, monitoring systems, for example, vibrations, different maintenance systems, reports, additional domain knowledge, etc. All these are necessary for creating a starting point for the intelligence itself. So the current available software is deployed on customer sites or in the cloud nowadays. Also, of course, I mean, depending on the regulations we may have, and may monitor and do predictions over one or even more and multiple sites. But having connected multiple data, this doesn't necessarily mean that you create an intelligent software automatically. So after the engineering step, a more important one is needed, which is the modeling. This step is trivial for creating the very first truth of the data. And only by having such very solid models and a good and fruitful monitoring will be possible. So what happens if such monitoring deviations are met? After the evaluation of the risk, the deviation might be important and needs to be integrated into further diagnostics. And into further diagnostics. Okay, having summarized this, we need to first do the engineering and clarify what is the historical data available. Then we continue with the modeling, where we can calculate correlations, which can give us a hint how we can create such a model. After we have created the models and we have validated them, then we do the go live, where we can monitor the assets via different models, where one or more models can exist for one asset, which is then including different sensors. After the monitoring step, we might have multiple sensors deviating. Then we can dig down and check the details of the sensors and do some risk assessment. And last but not least, we do the diagnostics, where we can have a look at the anomaly and check if something similar already happened in the past, where our algorithms also will be able to inform us about potential issues and resolutions. I think also here in one of the previous presentations, it was mentioned also about some prescriptive features here as well. Okay, so I have mentioned the experts, and so the experts are at the end of the day the ones who shape the artificial intelligence. And again, it's very good that I think we heard about this as well. That I mean, one of the perfect experts would be a combination, having, let's say, a data scientist with deep data-driven analytics knowledge combined with a domain expert in the different area, in order exactly to tackle these issues and solve these business-related problems, for example, in the petrochemicals. Okay, so starting with the case study on one of our sites, it is important to mention that before we start with the data analytics, it's critical to get a thorough understanding of the domain, the process, the instrumentation, with the help of our domain experts. So, for example, this can also be the operators, maintenance engineers, and so on. And then also utilizing and checking what kind of documentation is available, such as process flow diagrams, P&ID diagrams, showing also then the sensors that can be then later utilized for the data analytics. So for this case study here, we can see a P&ID diagram for a two-stage compressor. So on the other side, the data scientist, he will focus on understanding the data of the process or of the machine, with the scope of creating the models for example, for the anomaly detection. Typically, how we start with defining the data analytics tasks. And first of all, evaluating the situation, the input data which is available, and then coming to the data analytics tasks. In this case, the situation is that we do have several failures of equipment in a process plant, which leads to decreasing efficiency or even unplanned shutdowns. And consequently, what I just touched on at the beginning, again here, increasing costs. The input data is basically process and machine monitoring data of the equipment, which at the end of the day needs to be monitored. We're talking here about flow, temperature, pressure, vibration. And the final data analytics task is exactly then to detect these abnormal behaviors for the plant section, respectively, of the equipment before such failure actually happens, and then, let's say, to provide information to the operator how to, let's say, prevent in running into this failure, which could even result into an unexpected shutdown. So here's an example for a correlation analysis and a correlation matrix. In this case, this is for a compressor. So this is also this first step in familiarizing with the data, with the sensors available together with the P&IDs, which I showed earlier, and to select also the relevant sensors for the compressor. So we will have to identify the sensors with the highest correlation, and together with a subject matter expert, let's say the relevant sensors for the modeling, and along, let's say, with the most important modes of operation and the training periods, which are then getting defined. So here we see at the top, we see the dimensionality reduction data plot in order to reduce the number of input variables in this data set. So we can see here that we can find about 10 different clusters and patterns in the data. This can be then also associated as different mode of operations. Looking here at the data together with our subject matter expert, we do see 4 different modes of operation. And let's say looking at this time series data plot, we do evaluate and differentiate then between these different operational modes. In dark green, we may have here, let's say, one behavior during more of the winter time. Then in the brighter green one, we do it, let's say, in the early summer. And then in almost July, we see it then in the later summer. And obviously in sometime here in 2019 in March, we do have another, let's say, operational mode, which was confirmed that this has been some maintenance period, which was identified here out of the data itself. So how to select then the training data? So we do choose the steady state of the data of the running periods and use them as the training period. We may not maybe want to choose the training periods shortly before the shutdown, maybe also to avoid some learning of unexpected behavior that could have initiated a shutdown. So here we are choosing, for example, 7 different training periods between January and October 2018. Let's say to train our model for this case study here. So with that said, we build and engineer our models to monitor the compressor. So here, for example, we are building exactly 4 models. One model is for the pressure of stages 1 and 2. The second one is for monitoring the lube oil system. The third one is for the performance monitoring for the stage 1. And the fourth one is for the performance monitoring for stage 2. So, and here on the right hand, you can see how these different models are, let's say, built. Okay, so where you can see which different tags and sensors are included in which models. So this is then an overview of the analysis results, putting together the most relevant sensors, their anomalies, and the chosen training periods. Each of these parameters, you may see this, will have an estimated profile and an actual profile. The estimated profile is the blue line here, and the actual profile is the green one here for the different kind of sensors. And in the more of the, let's say, the gray one, which you will see then later on, maybe here it's better visible, is, let's say, the tolerance band which we have, which will tell you that this is the normal operating range for this measurement. And once, let's say, we have or we are exceeding this threshold, and an alert is going to be raised and the operator is informed. Of course, we're talking about, let's say, certain alerts and not, let's say, already some failures coming from the DCS system. This is then exactly, let's say, trained by our models and coming then from our models. So here we can see the different parameters and sensors which are part of the model for our lube oil system. So then here we do have one of the anomalies detected using our model for monitoring the lube oil system. So first of all, as you may remember, we were talking about different kind of data sources, including, for example, some maintenance log, and then, of course, validating this also with the customer. So the customer confirmed that he had had an issue with the lube oil system, and which resulted in an unplanned shutdown at the end on 31st of January 2018. And here on the right hand, you can see the different kind of sensors during this different, let's say, timings, which are part of the Model 2. You may remember we have, let's say, modeled these ones, and we can see the loop pressure, the loop flow, and the loop temperature are part of this Model 2. And as mentioned, so on 31st of January around 1:32, there was, let's say, this issue in the lube oil system. And with our algorithm, we have been able to detect this anomaly around the temperature of the lube oil system already 7 days, or approximately 7 days in advance. Again, you can see here we do have, let's say, the blue line is the estimated, let's say, the behavior, the profile, and the green line is the actual one. And in this more of the blue, let's say, drawing here, you can see that this is, let's say, the tolerance band. And at some certain point of time here, for example, you can see that this actual value is going out of this range, which is then resulting into an alert, which is then notified to the operator. So then another example for a failure for the lube oil system. Again, we are talking about our Model 2 with different kind of sensors for the lube pressure, the lube flow, and the lube temperature. Again, we do have, let's say, one maintenance log saying on 12th of March, approximately at 9:12, there was an issue also again with the lube oil system, where obviously there was some broken component in this one. And so also here, if we look from the data perspective on the different the timings here, approximately on 12th of March there was a failure, and then we already have been able to detect this issue several weeks in advance. Again, we can see here, for example, for the lube flow or for the lube temperature, that out of the trained normal behavior of these parameters, let's say we are getting a deviation, which is, let's say, then notified to the operator, and then again, would have notified him about this abnormal behavior already several weeks. We're talking here in advance. The third one is for the Model 1. If we maybe just go quickly back to show you for the Model 1, we are talking about the pressure of stages 1 and 2. This was the Model 1 with the different parameters what we have here. And then here again, so we do have on 23rd of October around 6:39 some issue with the corrosion. This was confirmed by the customer in the suction valve of the first stage compressor, and later there has been also, let's say, an issue due to a sensor break, where then at the end, let's say, this has been replaced. And again, our algorithms have detected a couple of weeks in advance before the failure happened, this abnormal behavior, and would have been able to notify the operator about this issue of this suction valve already in advance. So, summary. So we demonstrated that the models, they can generate early warnings for problems which could finally lead into an unplanned shutdown. This was for the first anomaly. They can also generate early warnings for broken components and even equipment deterioration, which have been shown in the anomaly number 2 and 3. So, key takeaways. I mean, at the end of the day, this means we need to have smart models. We need to create smart models with our data and the domain know-how. We need to rethink about the process to optimize our plant with the AI. We can maximize the asset utilization and prevent unplanned shutdowns via predictive monitoring. We are able, with this, as mentioned at the beginning, to improve operational efficiency and OEE, and at the end of the day, also to be able to run longer in a safe operation, where we also initially mentioned that one of the critical factors is exactly to protect our business and to run in such safe operations. So with that said, thank you very much, and I hope you got a good overview from our solution, and I'm happy to take also questions together with my colleague, Monika Heldinger.
Thank you, Fida. Thank you very much. Any questions to Fida? We have a question. So the question is from Raed Zaini, and he's saying that from the presentation, it is difficult from the pressure trends and valve, we can say we have component breakdown or take a decision to shut down the equipment based on that trend. So he's saying that the trend is not indicative of any failure. Based experience.
Yes. So yes, okay. Thank you very much for this question. So I think what I've shown to you is this is typically, let's say, the experts, and I wanted to focus on this expert, let's say, view. To look at the trend and then being notified. I mean, the notification, of course, this is something which is then coming out of the application itself, and then you can navigate down to the analysis, which sensors have been contributing to this. And this is the last part, which I did not show here in this presentation, but then also which can give you indications about, for example, a component breakdown using, for example, using our diagnostics feature. So to answer this question then, in the application itself, first of all, you will get a notification about this. You can dig down to this, and in order to support you, you will also get, based on previous learnings and previous behaviors, failure modes, you also will get, let's say, recommendations, what could be the potential root cause. I hope this answers the question.
This answers the question, indeed. Any further questions? Any case study related to stationary equipment or pipeline, critical valve, can it be shared with us? So maybe the case is not available right now, but Mr. Asrar is asking about if you have any examples related to stationary equipment that you could briefly highlight with the audience.
Well, perhaps I can take this. Hello, everyone.
Yes.
So currently, we don't have any study to show. We are having a project ongoing. The results are not yet available. So perhaps we would share it at a later point.
Okay, but the study you're talking about is for stationary equipment, yes?
Yes.
Okay, clear. Okay. I have another question. So for the predictive analytics you are providing, does it cover Siemens equipment or Siemens equipment and also equipment manufactured by other, OEMs?
Yes, so basically we can cover also other equipment than Siemens. So maybe I'm not sure if this is maybe a little bit was also part of this question. It's Siemens Predictive Analytics. It's mentioned Siemens Predictive Analytics. This is, let's say, we had it earlier. It was mentioned equipment predictive analytics. But as we are not only focusing on the equipment itself, that's why, let's say, we built another trademark for Siemens Predictive Analytics. So yes, to answer this, we would be also able to cover other equipment than Siemens.
Clear. We have a question about analyzers. So this is from, again, please, gentlemen, when you ask a question, try to mention your affiliation with your question. From Mr. D. Sagan, he's asking about analyzers. Any comments?
Monica, maybe if you can answer this related to analyzers.
I don't. I try to understand the question. So if it's a gas analyzer or something, so we didn't do anything in this direction currently, perhaps.
Okay, clear. Okay, thank you. Thank you again, Fida and Monica. Thank you very much for the great presentation. Now we will move to the next speaker, Mr. Flavio Pal from MathWorks. Byron, please unmute Flavio, and Flavio, please try to present your desktop. Mr. Mr. Flavio Paul will speak about predictive maintenance. Flavio is a senior application engineer at Computational Enterprise Simulation, CES, partner of MathWorks in the Middle East. Flavio has more than 7 years of experience in the field of artificial intelligence. Flavio, thanks for joining us.
Yes.
Yeah, please present your desktop and the floor is yours.
So hello everyone, thank you very much for attending to this event. My name is Flavio Paul. I'm a MATLAB and Simulink application engineer at CES, and I hope that the topics of the presentation will be interesting and insightful for you. So first, let me introduce CES and MathWorks. CES in Computational Enterprise Simulations is the exclusive partner of MathWorks in the Middle East. We are based in Dubai, and we are focused on working with commercial industries and helping them adopt MathWorks to enhance their workflows. MathWorks is the leading developer of mathematical computing software for engineers and scientists. It is a global company headquartered in Natick, Massachusetts, and with over 4,500 members and 31 offices, as well as many partner offices around the world. So these are some of our customers in the oil and gas industry, petrochemical industry, and utilities in the Middle East. They are current customers of CES and MathWorks. So we're going to get started by a quick introduction to predictive maintenance for those who are new to it. So what is predictive maintenance? Predictive maintenance starts with a machine. And in today's talks, we're going to talk about focusing on a pump, a piece of equipment almost everyone is familiar with. The pump has some sensor and which collect the data that looks like this. But what exactly does this data mean? If you have something like Google Translator for pumps, you'll be able to translate that the pump data and get some useful information out of it, such as the machine needs help. In fact, if you have a very good translator, you can get some information such as one of the cylinders pump is blocked and the pump will shut down the line in 15 hours. So look at these 3 sentences. I need help. One of my cylinders is blocked and I will shut down your line in 15 hours. The first sentence is whether your machine is operating normally. The second sentence is about why your machine is behaving abnormally. So there is a cylinder blocked. There is maybe some kind of leakage. And the third sentence is about the time to failure. So how long can you continue to safely operate your machine? The first question we call anomaly detection. When you're trying to detect anomalies and you see if there is a variation from normal behavior. The second question is to answer is the condition monitoring, when you are continuously monitoring the state of your system and to see if there are anomalies or faults being detected. And finally, the third question is about remaining useful life estimation. So that's helped you to understand when your machine is going to fail. These are the questions that predictive maintenance helps you to answer. And predictive maintenance toolbox in MathWorks helps you develop this algorithm. This toolbox was released in 2018, and today we will talk about its functionalities. So how exactly are MathWorks tools used for predictive maintenance? There are 2 companies in the oil and gas industry. They are using MathWorks tools today for important applications. Oil and gas industries have strong safety requirements, as you know, and any issue with these systems can potentially cause a serious damage to equipment and even human life. And here is what they have to say about using MathWorks tools for predicting maintenance, like Transocean's subject matters expert familiarity and State Oil about MATLAB popularity within the company. These are two key things we heard from a lot of engineers who use our tools across the company. And when they use our tools, they develop algorithms and they have a better experience. So also we'll talk about some cases for companies like Safran, Mondi, SNCF, Mercedes-Benz, and Bosch are all using MathWorks tools today and for developing these predictive maintenance solutions. So how a workflow for developing a machine learning algorithm with MathWorks looks like. Start with acquiring data, reprocessing it, identifying some features from the data, training a predictive model, and then deploying and integrating. There is then a feedback loop associated with the deployed model that sends data back into our system to further develop algorithm development. Now, one thing you might have noticed is that there is some iteration that happens when you evaluate features and training predictive model. So you tend to go back and forth to figure out the best features and the best predictors for the model. One thing to note is that machine learning only plays a key part in one step of the workflow, is the training the model. So why you should be using MathWorks for predictive maintenance? It helps you to reduce the amount of data you need to store and transmit. It enables you to explore different approaches to feature extraction, predictive modeling. It allows you to deliver the result of analytics based on your audience. And finally, you can get started quickly, especially if you're an engineer. So let's go to the first point, reducing the amount of data you need to store and transmit. And they started with 3 steps of the workflow. With the acquiring the data, reprocessing it, and identifying the features. So why exactly is this important? Well, if you think about a common challenge that you might face in making sense of all the data is being collected. So if you think about the pump, one sensor operating 1 kilohertz, so 1,000 samples per second, generates about 60 kilobytes of data in 1 second and 1.3 gigabytes data in a day. And for a pump with around 20 sensors, that translates to 6 gigabytes. As you would expect, I don't have just one pump with 3 pumps on site generating 78 gigabytes of data a day. And this is how expensive it can be to transmit the data if you're using satellite transmission. If you're using cellular transmission, it's 1,000 times less, but it's still a lot of money. So we are dealing with a needle in a haystack problem. How exactly are we going to look at 10 gigabytes of data every single day to detect anomalies and detect faults, detect and remaining units of life? So, and that's why feature extraction is important. But it allows you to reduce the amount of data you need to store and transmit by allowing you to focus on the key elements of the data or the aspects of the data that give you more useful information. So how do you store these features? You use signal processing methods or statistics and dynamic modeling methods to identify these features. So how do you identify which features to extract? That answer really depends on the data you have available, as well as the hardware you have available. And finally, how do you deal with the streaming data? Most of you have data that's coming in a very high rate. So when you're dealing with such a data, you have to determine some kind of buffer size and extract features over this moving window So you are able to reduce all the data you see over this window down to a small table that you see here on the right with some features. So how exactly methods can help you to do that? Predictive maintenance toolbox has a new app called a diagnostic feature designer that allows you to explore and discover different feature extraction techniques without writing any MATLAB code. So you can extract, visualize, and rank features, use different approaches, including statistics in dynamic modeling, and even work without memory, without data in memory, so data in disk. So let's take a look on how you can accomplish to detect anomalies using the diagnostic feature app. In this video, we will see how to analyze some time domain flow data from a pump and find out if there is any way we can detect anomalies. So as you can see, it looks very noisy. The spikes in the data clearly indicates strange behavior, and it's weird if these spikes are periodic or random. Looking at the data in the time domain, even if you zoom in visually, it doesn't seem to help finding patterns or any strong deviation. There is nothing we can detect visually. So we estimate the frequency spectrum of the data we have, and here you see if we analyze the data and find any information there, we specify the model order and for the and also where to fit and plot it. And when you do this, you are able to extract all the frequency spectrums without writing any MATLAB code. You can see that there is some strong periodicity involving this and there are some frequency peaks. Now, if you zoom in, you can see peaks. You can see two different types of variations. One, you see the region when it has higher free power range, where points are very closely accumulating together. They may indicate good behavior. And also you see the second range of frequency peaks that are more widely spread out, and this may indicate anomalies under here, these peaks. So by looking at all this time domain data, we just extract the frequency peaks, and then try to categorize them to see what their values are. So if there is an anomaly in our system, we can detect using these features. Daimler, Mercedes-Benz are using MATLAB today for anomaly detection in a similar way. By looking at the data, they have different features, and then by seeing how these features vary over time and over magnitude, this is the way how Daimler reduced the amount of data they are storing by the factor of 250. If you think about when is all this data that you are collecting the most valuable, think about the time along the x-axis. If you are processing historical data that has been collected and is a couple of days of month old, you can use this data for training the algorithm. Time critical decisions can be based on data coming in seconds, minutes, or hours. And it's when you have a lot of more value from your data, because now you are able to look at the data coming in and say, look, like there is a fault in the system, let's stop operation before failure actually occurs. And real-time decisions is where you have the most of your money, because you are not waiting for your system to make a decision based on data that's being collected, transmitted, etc. Collecting this data and making a decision in real time on the machine itself, using devices such as PLC and embedded controllers, and you are able to make decisions before you have to go to another system or wait for the operator to get there. So So in this example, we are looking at some feature that we extracted in the previous case, but instead of we are looking at the code, taking into account the concept of buffer, it's storing a bunch of data and as it comes in, and it would be resampling the data and on the periodic time base, extracting certain values like such features like peak values, mean values, etc. Once you're done with that, we can take this MATLAB function and generate C and C++ code. Automatically, we can detect. We can even target certain hardware devices for which C and C++ code is customized. And now with this code, you can deploy it on the embedded device and have real-time decisions. So the next step that I'd like to talk is how MATLAB and Simulink allows you to explore different approaches to feature extraction predicting modeling. So why is this important? If you think about the pump we were talking about earlier, a classification algorithm will allow you to identify the root cause of the anomaly. So this is a 3-phases pump you see quite commonly in drilling and servicing oil wells. The 3 plungers should have a uniform flow. Now there are 3 types of failures as possible in this case: a seal leakage, a block inlet, or a bearing degradation. But we don't have sensor for all these, all 3 of these components. Instead, we all have some pressure and flow sensors in the outlet, and we have to analyze the data coming in on this sensor and see if any of these faults is present in our system. The purpose is to detect 8 faults only using 1 sensor for flow data and pressure. For some of you might be thinking, what exactly I do if I don't have the failure data? Because what you're trying to make sure is your system not to fail, right? So sometimes you don't have the data. So in this case, you can build a virtual model of your system in Simulink or Simscape, and then generate synthetic data, which models these failures and can be representative of a real failure behavior you might see in the field. For this, you will need to inject failures using experts about the equipment. So if you generate a lot of synthetic synthetic failure data from a pump model, we're trying to account like 8 different fault types possible in this video. And we have a bearing fault, a blocking fault, blockage fault, and a leakage fault. So once you have done bring the data to diagnose feature designer, allows you to extract domain features at a click of a button. So you can simply select all the features you want to calculate and then click on OK. When you do this, the app automatically looks at all the data sets, compute the features, and then stores them on the table in plots. So what you see over here is a distribution of the fault of the feature values based on the fault type. So if you see certain features being very widely spread out, is for different fault type, that's indicate that's a good feature. Also, you can extract some spectral features as well. We indicate the range of the frequencies, then that we want to extract some features, and then we can extract things like p-values, band power, and the model coefficients. In this case, we are extracting 5 frequency peaks. Once again, if you click on OK, all of these features are added back to the feature table we spoke before. I told you before. So you have histograms of the feature distributions. So we didn't need to write any code or extract any features. So when you look at the feature table, is exactly what you see in the video. You can then rank these features to see which feature is more important. The larger the importance of the feature, that indicates a better predictor for the classification model. and that can be used for detect which fault is present now in your system. In this case, we choose the top features and then directly export them to the classification learner app, where we can train multiple classification models to see the best fit. In our case, we train a bunch of solvers for ensemble and get the better results, 80% among the best result. And we can then fine tune the classification model to get better results. But what I want to show here is that without writing any MATLAB code, we were able to analyze data, extract features, rank them, train a predicted model, and export the predicted model as well. So a part of the classification algorithm, you can also train a remaining useful life algorithm, which can help you determine when your plant is expected to fail. In this case, we are training a degradation model. As you see in this gradation model, we have a safety threshold that we are trying not to cross. Baker Hughes is using MathWorks tools to develop a prediction model, and they were able to look at the nearly a terabyte of data and create machine learning model that predicts the failure before it occurs. They use signal processing and machine learning techniques to extract these features and predict the failure. These have enabled them to save more than $10 million as projected value. They are deploying these models on the track they are using. So and this enables them to take decisions faster. So the next step of using predictive maintenance algorithm is delivering the result of this algorithm to the right audience. So this is when deploying your analytics is really important. You need to deliver the right result to the right end users. Otherwise, you won't see a lot of benefits of predictive model algorithm. And different end users have different requirements. Like, for example, maintenance needs simple and quick information to get started, handling the devices or alarms. Operations needs to have bird's eye view, so they need integration with IoT systems and understanding of how the overall system is operating. And if you are the manufacturer, your end customers may be expecting some automated report or some easy to digest information that helps them to understand how their equipment is performing. If you think about a common workflow or a common application that many people have today, they want to have the predictive maintenance algorithms running on the cloud. In that case, there is a system architect and their desired devices. The system architect is responsible for creating this entire production system. The production system is getting the data from these edge devices, these assets, using things like Apache for streaming data, using data storage like Elastic. And MATLAB production service the ideal way to run your predictive maintenance algorithm in this production environment. So you can have your algorithm developers working on their desktops in MATLAB, creating this algorithm, and then deploying them using the MATLAB compiler. And you can also take the end results of this algorithm and deploy them to make an integrated visualization with business in platform like Kibana, where your end users can have access to this information and information from other systems as well. So that enables them to make decisions faster. And notes that Lab integrates with a number of different platforms. So cloud storage platforms, streaming systems, and dashboards. So in MATLAB production server lets you do all of this. Bosch and CNCF have implemented MATLAB production systems running for predictive maintenance today, algorithm today. If you see what Bosch is saying, they are talking about updating software in just one location and a maximum of 1 hour downtime to make all these major updates across the entire system across multiple countries. And SNCF, sorry, it's a French manufacturer. They are talking about bit by bit incrementing their existing solution for maintenance using MATLAB and MATLAB production server to integrate this algorithm for predicting failure and detect anomalies. CS has an ongoing proof of concept with Chemia. The objective is to predict the faults of one cylinder of the compressor. We work in the part of the pre-processing data. The data cleanings, every predictor have 1,000,000 elements, so we have 20 predictors, so we're working with 10 million elements. We need to work on the labeling, the faults, and also visualizations and analysis. We trained the model using sample methods. We got a very good accuracy. You see in the screenshot of the classification learner. And we tested also with a sync data and was very good answer. Some of the faults doesn't have a lot of labeling, so this is what some of them doesn't reach a good accuracy. Next step is to classify the sequence of data using LSTM networks for time period in the future. So we want to see if we're gonna detect a fault in the next week. And also we want to integrate in this solution to the Chemia and DCS system. And finally, to keep benefiting of our MATLAB and Simulink, using MATLAB and Simulink, it allows you to get started quickly, especially if you are an engineer. Methods can help you to get started quickly. We have examples to talk about creating a predictive maintenance algorithm for pumps, motors, gearbox, common type of equipment that you'll be dealing with predictive maintenance today. We have documentation that explains the concept of predictive maintenance, explain which are the type of feature extraction methods, what kind of predictive model for detecting remaining useful life, fault classification, and so forth. So we can help you conduct your tutorials and workshops that explain these concepts to you and to give you a hand on this field on what it looks like to develop this algorithm in MATLAB. Finally, we have some consulting services to help you get started with a proof of concept and also we have Tech Talk series. It's our video series that help you to understand the concept behind predictive maintenance. In some MATLAB and Simulink helps you to...
Thank you, Flavio. Could you please try to conclude in 1 minute? We are running out of time.
Yeah, I reached the last slide. So this is what MATLAB helps you in summary, and we are now open for questions.
Thank you very much, Flavio. Very informative presentation indeed. Any questions to Flavio? This is a great actually presentation. Most of the audience from the industry, and this is a good opportunity to have an idea on how to process data and some of the tricks behind that. So this is a great insight indeed for all of us. Any questions, gentlemen? Okay, maybe the questions will be forwarded later to your email.
Yes.
You have Flavio's contact. Please register them. If you have questions, you can email him later on.
Well, it looks like we did have one from Raid from Yansab.
Oh, okay. I did not see that.
It says, when we talk plant data, are we talking about 10 seconds average, 1 minute, 1 hour, longer average will hide issues from our experience in the plant?
Good question. The resolution of the data depends on what you have available. If you have more resolutions, every second is better. So we can work with all of this. So we don't have limitation with big data. You can bring all this data to MATLAB. We can start with a model with data every 10 seconds, and if you have a good result, or you can move to data every second. So it depends on you can try all of them.
Okay, depends on available data, basically.
Yes.
Okay, yes. Clear. Okay. Thank you, Flavio. Now we'll move to the next presenter. We move to Pavel. We hope the issue has now been resolved with Mr. Brak again. Mr. Brak is from Russia, and he is the regional sales director for Russia, Middle East, and Africa. Pavel?
Yes, do you hear me now?
We do hear you, yes, loud and clear. Great. Please share your presentation and proceed.
So good afternoon. Once again, I will talk today about simulation-based digital twin for predictive maintenance. And before we proceed to the topic itself, I just would like to give you a quick introduction of what we are doing at ANSYS for digital safety, because this digital twin is a part of our digital safety platform. And you probably know that ANSYS is a company who is providing software for 3D physics simulation. But on top of that, we are also doing digital safety applications, which are all together combined in a single digital safety platform. So these are applications for model-based systems engineering, model-based software engineering, and model-based system safety analysis, which also includes the safety analysis for process industries. And digital twins is one of the topics in this large picture, and I will concentrate today on the simulation-based digital twin, how we call it at ANSYS. And you probably heard a lot about digital twins. Is a kind of the hype technology now. But if you would Google for digital twin, you probably will find a lot of different explanations of what basically it is. And in most of the cases, you will find the definition that digital twin is basically the data science digital twin, when you have the physical asset which has the built-in connected sensors which transfers the data to Internet of Things platform, and this data you can then analyze, and based on your data science, based on your statistics, based on your analytics, you can analyze this and make certain decisions on what you are going to do with all of this. Are you going to use it for predictive maintenance, or are you going to use it for any other business cases? And in many cases, this is actually enough. So what we introduce here, so we are adding here the engineering data to that platform. Based on the information we take out of the virtual model of that particular physical asset. And here it's very important to understand that it's not just the generalized engineering data from the generalized model, that's data from the model which is built by reflecting exactly the situation and the particular physical asset, which means that the data you will feed will repeat and represent what is happening actually in that particular physical asset. And this is what we call simulation-based digital twin. I will elaborate a little bit more about that. So as I said before, the data science-based digital twin is sometimes works very well for certain activities. Here, for example, on that picture, you can see that there might be a pump installed somewhere in the desert or in the forest or in the North Pole. And this pump can send you the data to your IoT platform. And with this data, you can just see, okay, there was some vibration in this pump, and this vibration increased 2 hours ago or 2 days ago. And you can understand what is happening, you can understand when exactly it is happening. But for sometimes that's enough. But for some activities, particularly for the activities which are connected with the safety and the activities connected with the very expensive or important assets or assets which are operating under different conditions in different environments. So that might be not enough, because you not only need to know when and what is happening, you also need to understand why it is happening, and you need to understand how it is happening. And this is where simulation comes to help you, because simulation, physical simulation, is exactly the answer on these questions. And the questions are, as I said, this helps to answer why something happens. For example, on this picture, there is a T junction, and on this T junction, there are some temperature readings downstream are too high. And I can read this data from the physical asset. I can make a simulation on my digital twin, and I can answer on different questions. So I can answer why are some of the temperature readings are still too high, and why are some of the mixers failing more often than others, and so on. So this helps me to answer why something happened. And also, this technology is helping me to answer how it is happening. For example, I can, by making the upfront simulation, I can understand, for example, how I can modify that particular mixing strategy in this mixer to fix the issues. And once I made these modifications, how much longer I can expect this to last in the field over the variety of conditions. So this, all this allows me to extend my lifetime of the product, to optimize its lifetime, to optimize maintenance, repair, and overhaul operations, and to save the money, obviously. So how do we reach that? We reach that with two technologies. So first is virtual sensors. Virtual sensors, that's the basically the sensors of different kinds, like temperature sensors, vibration sensors, radiation sensors, EMI sensors, which I can install inside my digital twin, inside my model, and I can provide with this, I can get additional information to what I can obtain from my physical asset. In a physical asset, not everywhere I can install these sensors. Maybe the sensors has not been planned by design, or these sensors is impossible to install in that particular place. So the virtual sensors allows me to augment my IoT data. It allows me to provide the real-time information based on that IoT-driven digital twin calculations. And second thing, very important, is, as I said before, it's a what-if scenarios. And what-if scenarios, that's the way of simulation when I can simulate my my model, my digital twin, to run the simulation upfront. So I can say, okay, if this picture will continue to work like this, if this vibration will continue for next 2 days or 2 weeks, so what will happen? What if this will continue like that? Will it be? Will it lead to the efficiency? Will it lead to the maybe this part can be destroyed? And I can plan my optimal maintenance and operation activities based on this information. So just to summarize on what is a simulation-based digital twin, this is the definition how we understand this technology at ANSYS. So simulation-based digital twin is a connected virtual replica of an in-service physical asset in the form of a multi-domain system simulation that mirrors the life and experience of the asset. So the idea is, as you probably understood, that I need to have as many digital twins, as many assets I have. For example, if I have 100 pumps installed somewhere on the factory or in the field, I will have 100 digital twins. So each digital twin will represent the exactly a certain pump with a certain serial number. And it will work in parallel with this pump, and will continue and will repeat everything what is happening inside this pump during its lifetime. So how do we achieve that? We achieve that by introducing two key technologies. So first technology is a technology of reduced order models. A reduced order model is a simplified model of a high fidelity dynamical model. Here, for example, you can see on this picture. So there is a model of a junction made at Fluent CFD, and it takes 3 hours to calculate on 12 cores. The same reduced order model with nearly same accuracy. It runs real time, which means if you can make your digital twin build out of these several reduced order models, this allows you to calculate everything nearly in the real time, which means you can repeat exactly what is happening at your asset in the real time. The second technology is the so-called simulation integration backbone. So this is where we actually bring all these models together on a single platform and connect these models the way that the input and output data from each model, they are interoperating with each other. And this is how you create the multi-physics simulation digital twin. So you bring the models from different applications, from different physics all together, and it can work all together in a very fast and efficient. So just to summarize, the first part is that we basically simulation-based digital twin can be built across process industries, value chain for critical engineering systems, nearly in all areas of activities. So in downstream, in upstream, and so on. Now let me just give you some use case examples of applications of simulation-based digital twin for you to understand what the implementation can be. Most of these implementations are working now in the real life. Some of them are under development. Some of them just on the very initial stages, but you probably need to select your own business case and to understand what are the benefits and what would be the model which will be required for you. So first example is an example from a company called Flowserve. So this is the digital twin of the fluid pump. So here you can see on this picture there is a digital twin built out of the 3D reduced order model from ANSYS Maxwell, which is electromagnetic simulation, and ANSYS Fluent, which is hydrodynamic simulation. And with these models, you can make the complete simulation of the operations of that motor. And the key target was to minimize operational service issue, which was related to suction blockages, pump cavitation, and motor overheating. So this way, you can get the data from the real pump. You can run this digital twin, and you also see here the screen with all the parameters, and you can control this digital twin by your own. And this all connected on the PTC ThinkWorks Internet of Things platform. So the benefits are the optimization of operations, of course, and the operational insights for all these virtual sensors. Another interesting example, that's a General Electric Digital Foundry. This is an offshore wind turbine, and inside this wind turbine there is a set of motors, and these motors is very difficult to maintain because they are very high in the tower. They are located very inconveniently, and you need to plan your maintenance up front always, and it costs a lot of money. So the idea was to be able to predict maximum temperatures in the motor to prevent unnecessary maintenance actions, and to predict and optimize the motor life of that motor. So here you can see there is a digital twin model. It's a simpler model which consists again of the 3D reduced order models from Maxwell and from Fluent, and for detailed motor thermal model connected with GE Predicts IoT. And the benefits are to reusing the existing models, to reducing maintenance costs, again using the virtual sensors to predict, monitor and manage maximum temperatures, and to basically transfer these activities to the predictive maintenance. Another example is ESP, that's electrical submersible pump system, which is very popular in some process industries applications. There are more than 100,000 of such pumps are operated globally in oil and gas upstream operations. And the key benefits to get the digital twin of that is to predict and improve asset performance, asset reliability, to improve maintenance decisions, and to increase operational efficiency. So here you can see how the digital twin systems combination look like. So on the left side, there is a system digital twin, which consists of the pump model, of the motor model, thermal model, and also the 0D representation of all components. In the middle, you see a human-machine interface to that particular digital twin, which is connected with SAP PEI platform. And you can control this submersible pump, this digital twin, and you see the results on the right-hand side, what you actually get out of that digital twin. And there are many of such examples I can do. I have a limited time, but I will just go quickly through a few other slides, which are, for example, here you can see the blow-up preventer. And blow-up preventer again is a very critical part of the operations. You need to be able to maintain it properly. You need to be able to predict all maintenance activities, to detect the problem, and to make it working correctly. So the digital twin is a very good application here. It allows to to detect the problem very early and to reduce risk of failure over many hours up front. Another example from the company called Verbund. This is the complete digital twin of the water turbine, where the idea was to predict the wear on the turbine under different loading conditions to optimize output and plant downtime. And the solution was, again, the simulation-based digital twin and surrounding components. This was connected with physical sensor data to IoT platform. And the result is an optimized operations of the turbines, which saved around 100K per year per turbine. So this was a very significant savings out of this implementation. Many other examples, as I said, just to quickly name it. So there are erosion of pipelines, fittings, armatures, then different components of the plants or upstream and downstream operations, like, for example, desalter. You can see here very big value of digital twin implementation. Crude distillation unit, an example we received from Indian Oil. You can see here also simulation-based digital twin implementation. And there are various smaller applications, like, for example, filters, like, for example, drill heads, drill strings, different kind of valves. Then it can be different kind of pumps, as I already mentioned. And the last, what I would like to show you is this. This is the concept of the digital oil field, or it can be digital petrochemical factory, or it can be digital plant, or digital energy plant, whatever. So here you can see there is, it starts from A on the lower left corner, where we do that data collection from the physical assets. Then in this data, together with maybe even high fidelity models, but also with reduced order models, it's and embedded software, so it's simulating. And we have a predictive physics-based models. So then this data can be also fed to the special set of applications which also supported by this digital safety platform, which is responsible for safety inspection and failure mode and effects analysis. Then it also can be fed into the failure prognosis and CBM, and then feed back to the decision-making system, and then in order to update to make decisions and conduct what-if scenarios. And then now the circle is closed. So this is kind of the all life condition monitoring of that particular example. Yeah, so I think that's all from my side. Please, if you have any questions, I will be glad to answer.
Thank you, Pavel, for a great presentation. Thanks also for accepting our invite. Any questions to Pavel?
We do have one from Sabri. It says, in your simulation, is the chemical reaction causing heat release can be modeled in order to analyze the temperature change?
Oh yeah, absolutely. So anything where there is a physical solver exists, so everything can be simulated. So in fact, I think that there are no physical processes where there is no solver right now. So which means that you can, to a certain extent, depending of course on the mathematical implementation of the particular solver, you can simulate nearly every physical event with these models. And moreover, it's not just a single physics. So as I said before, the key idea is that there is a multi-physics simulation. So you can analyze how different physics are influencing each other together, like hydrodynamics or heat transfer and AMI and so on.
Good question. Any further questions?
I can read it. So if we have ANSYS on our PCs, how easy it is for us to add the twin models to need any additional hardware software. Yeah, so we have a special application for creating digital twins. It's called ANSYS Twin Builder. That's the separate application you need to install. And this is application which allows you several things. First, it allows you to create a twin. Means it allows you to bring models from different ANSYS applications, or not necessarily ANSYS. It can take models from other systems. then you can create and generate reduced order model out of it. And then you can bring it all together and generate the digital twin. So this is the development phase. And then this application also supports so-called deployment phase. So when this digital twin is on the operating phase, so when it is running, so you can produce a runtime model of digital twin out of this application. And this will be a kind of the executable file, which will accept the input data, and it will feed output to your IoT platform or to any other system. So yes, so the answer is yes, you need to have ANSYS digital twin software, and this is the software for working with digital twins, both for development and for operations.
Okay, thank you. We have maybe one more question from Asrar Muhammad. Is it possible to do the simulation for non-metallic underground pipe, RV pipe, to understand ongoing damage and corrosion barrier or estimate remaining life to develop strategy?
I think yes. I cannot promise you because I'm not very familiar with that particular physics, so I cannot tell you exactly if this is what kind of data is required. But yes, as I said before, for that kind of physics, we have solvers, and these solvers can do that. Yeah, and the only question here for digital twin implementation is how do you get the data out of this pipe if this is underground? So if you have the way, so there are two parts. So simulation, yes, we can do simulation. And we can simulate corrosion, we can estimate remaining life, and so on. The question is, how do you get real-time data, or not necessarily real-time, how do you get the data from the certain part of this pipe to the system? So if you're able to transfer this data by a certain kind of sensors, if the sensor has already installed, so you need something to compare with. Right. If this is possible, then yes, this is quite doable scenario.
Okay. Thank you again, Pavel, for addressing the questions. Now we'll move to our next speaker. We'll move to Mr. Ronald Weeks. Ron is a solution consultant in Honeywell Connected Industry. Honeywell Connected Industrial, a part of Honeywell Connected Enterprise, a strategic group of Honeywell tasked with evolving, developing, and delivering software into connected value-adding digital tools. Ron has over 32 years of experience in the specialty chemicals, petrochemicals, oil and gas, and energy, and other resource industries. Thank you, Ron, for joining us. Ron will be speaking about asset performance and inspection 4.0. So he will be delivering a talk covering two topics. Ron?
Hi there, Aldo Motion. How are you doing?
Very well. How are you? So you will
okay.
present. You will combine two talks in one presentation, or you will have them like
no,
separate?
I'll have them split. So we'll start with the predictive maintenance one, and then we'll go into the workforce productivity.
Okay. Yeah. Please proceed.
Yep. Okay. Well, thanks again for offering us the chance to present at this event. Obviously, there's been a lot of talking on predictive maintenance today, so I know a lot of the content that I'm about to talk about most likely has been discussed previously. But let's take a stab at it and see if we can add any additional context to your perspective. The agenda that I'll run through is first look at the APM industry space, APM being asset performance management, and then the key challenges that we're essentially trying to resolve from a company perspective, and I think from an industry perspective as well. And then a quick overview of the APM environment, some of the general features and functions that most likely you should consider when you're looking at any solution in this area. An idea of the APM strategy. There are different sort of strategies you can take. I'll go over one that we take, and maybe also give a quick example, what I call leading by example, which is eating your own dog food, we call it, because we apply this technology to our own manufacturing processes. Honeywell has its own manufacturing plants for polymers and things like that, and we took this technology and we applied it on our own assets and some of the results we obtained from there, and then a quick Q&A. So with that, in terms of the APM industry space, this is one space that has evolved over many decades. This is not something that recently has come into the sphere of our discussions and things like that. There are many well-evolved point solutions in this area, but what it all points to is that they do not normally handshake. They do not normally talk to each other, do not normally integrate with each other. APM going into the future needs to unify, align, and draw deep insights from all these solutions that are essentially out there. These can be digital twins, we've talked about that, maintenance management systems, predictive analytics systems, which includes machine learning, reliability analytics systems, mobile applications, which allow workers to interact and use this technology in the field, condition-based monitoring system, vibration systems, and process historian data mining systems. So it's incumbent upon us when we actually look at this technology and how we can actually use it to our greatest benefit is to first take stock of what we have in-house and how we can exploit the value, increase the value from integrating them together into the future with an alignment along the significant developments that we've had within the predictive analytics and machine learning area. Now, from our perspective, we believe there are two challenges, really for Honeywell, there are two challenges we're trying to resolve within this area. There's the human capital challenge and there's the operational challenge. Human capital challenge being, we see it within your industries, you see it within your industries, there's a lot of experience loss. People are retiring, you have a very high demand on the subject matter experts around these assets. Your people are stressed because we're all pushing for better productivities out of them. There's tons of what I call manual calculations and Excel hell that is out there that our people have to deal with. And in general, there's a perspective that, a maintenance approach should be a run to fail, depending on, the asset in question. Then there's the operational challenge, which looks at, profit loss. As we know, we have applied many technologies over the last few years to try to, implement Lean, Six Sigma type approaches, operational excellence. So it's much harder to grab additional value out of our assets in these areas. We have the capacity constraints issues in terms of unplanned downtimes and bottlenecks that we face. And generally, even though we have all these systems, we have a fragment view of what is out there. It goes back to the first topic that I talked about, the many systems that you have out there, but they're not really connected or handshaking. And lastly, in operational areas, the safety risk that we always have to be cognizant of because, within the industry, whether it's chemicals or mining or petrochemicals, safety is number one, above all else, full stop. So these are the sort of challenges that we face, and we think that through a concerted APM effort, combined with your existing legacy systems, we can most likely try to meet these challenges as this circles around human capital and operational areas. Now, from a solution perspective, I think from our previous speakers, we all know about the four main things that we want to do when it comes to asset performance management. We want to collect data. We want to analyze that data. We want to put it in a good context where then we can detect impending issues with assets, inefficient energy usage by assets, and further on identify improvement opportunities within assets. Once we detect these things, then we want to give prescriptive recommendations to the users, or at least ideas on how they can improve or mitigate the problems that they see. We tend to take a different approach, and this is approach that a lot of people are following these days. But from the inception of our product, we focused on what we call performance models. And our platform was purely a performance model-driven platform up to about, let's say, 4 or 5 years ago. And then we decided to bring in the machine learning angle, because we identified there was an opportunity there. So from the get-go, we saw the requirement for an amalgamation of these types of models, a performance model and an analytical model. And then you layer on that the mechanical health models, which take into consideration typical applications that we've used previously, like the vibration models for time waveforms and spectral data. And you have a very holistic environment. And that is what we're shooting for, and it's what we have within our platform. A holistic environment where we bring together many models to essentially solve differing problems, because no problems are the same. Even within a specific asset, it depends on how it's being used and how it's being operated. So from a very high level, we believe there are about 5 areas you need to really concentrate on when you're looking into this technology. And those 5 areas are broken down in front of you into data collection and processing, model data analytics, contextualization, visualization, how you process events, and the technology that you use. So take heed that when you're actually doing data collection, it's important that you start to stick to standards. Obviously, OPC is something that we've accepted over the last few years, and it should be a basis on which you build your data collection methods and protocols. But not all data is temporal, and OPC deals with purely temporal data. So you do need capability to have relational database access to grab relational data. You need to use one of the most hellish tools that we use today, which is Excel. So you have to have the capability to utilize data that comes from Excel. And on top of it, you have to have really good data cleansing and validation processes. Within the model and data analytics perspective, because we take this approach of a multi-model approach, performance data-driven approach, we believe definitely within the model and data analytics, you need to have some sort of advanced thermodynamic performance models embedded within these tools. You need to have the process data analytics and then predictive machine learning to bring in the data-driven aspect. And another aspect which you can also use, but maybe to a lesser extent, because what you really have to do is really define, why you need to have such a rigorous approach, but it can be helpful, is bringing in what I call process simulators, which can run, short simulation models, or even running the process simulation offline, perturbing it several areas, and then bringing that data in as a data set to be fed into the models. And the last one is fault and symptom models that we believe that is required. So just make sure that you check off these things when you're looking at, the solutions that are out there that they meet your requirements. In the area of contextualization and visualization, we believe that you need to have a very thorough real-time asset status dashboard. Now, what does that mean? It means you need to have specific things that can guide the users to events and problems very succinctly. One of them is that we all use, and I think I've seen it in a lot of the solutions that have been presented, are tree and heat maps. The other area that you need to be also cognizant and take heed around is around data and KPI trending. Because not all KPIs will be in the solution, there might be a need to calculate KPIs offhand or aggregate KPIs across assets to look at maybe a process unit, the health of a process unit. So there needs to be a very good KPI trending and calculation engine embedded within the solution that you choose. When it comes to prediction and remaining useful life, some people say remaining useful life, others talk about TTF, time to failure. This should also be a part of your analysis and your requirements within your contextualization and visualization requirements. Because we're also dealing with performance models, it's also important to bring in the asset performance curves of the assets that you're looking at, specifically around rotating assets, which might have performance curves, pump performance curves, compressor performance curves. It's important that you overlay and be able to overlay the current operating point versus the design that the original equipment manufacturer has taken into consideration, so that you can see whether the asset is running at its best BEP, best efficiency point. And combined with the visualization and stuff like that, you need a fault tree and event history capability within your contextualization and visualization capability. Second to the last requirement is around event management. There you need to have an extensive event monitoring and grid analysis system within your platform, so you can track the events, observe how frequently they come up. You need to have an event fault tree. You need to have the capability to do fault reports. You need also the capability to notify users, whether that's through email, whether that is through a pop-up on a screen, or whether that is through the most common means, which we all get notifications today, through the telephone, through an SMS or pop-up notification. And at the end of doing this all predictive analysis and and maintenance and things like that, there needs to be that connectivity to the real solution which drives your operation, its processes and things like that. And that's the maintenance management system. It needs to be able to connect to those systems, whether that is an IBM system, whether that's a SAP system. You need to have that capability to have that connectivity within the platform for that purpose. And lastly, in this area of event management, you need to have capability to drive operator alerts and advisories so that they can take action as fast as possible as they are the front line in terms of the operation of the plant. In general, around the applied technologies, definitely you also should take in consideration are things like HTML5, zero footprint on browsers and PCs, because this will allow you the capability to upgrade the solution without having to touch the user significantly. You need to also have the capability for multi-browser compatibility. We all use different browsers today. On my PC right now, I have 3 browsers open. I have Firefox, I have IE, and I have Google Chrome. So for a solution, it should be able to work in any environment, because we're always switching and we're always trying to optimize our operations in the way how we work. It also needs to have capability for complex event processing. It needs to be able to also take in models that it did not create. We had a very good talk by MATLAB, okay? And if they can generate a MATLAB code for a specific model that you develop, the platform needs to be able to take that model and execute it as well. Whether it's MATLAB or whether it's Python, we focus on Python specifically. In the area of single layer or security, it needs to have SSL support, single layer support. And in the area, if you're looking at things like running these systems in the cloud, you need to have a very secure means of moving the data, end-to-end encryption between your site and the cloud. And lastly, I think I talked about it in the first topic, which is around data collection and processing. We tend to use Matricon OPC because they're very standard. They have connections to almost DCS out there and systems out there. And we tend to focus on using the OPC UA support, which is the next generation of OPC UA, which all vendors should really try to drive towards, or I should say operators. So in terms of the APM strategy, let me just check my time, 3 minutes. In terms of the APM strategy, we tend to essentially focus around, as I indicate, a multi-model system, a physics-based system, and this is the performance models using thermodynamics, thermal performance models, a heuristical system using rule-based, and a machine learning system. We bring all of these together to create alert management analyses. Now, in terms of the data flow, you would have the data that's sitting out there. You have your OPS connectors that's pulled into the system. You run your first principle and your thermal performance models. At the same time, you also do your anomaly detection models. Those three feed into a diagnostic system, and that diagnostic system then can produce alerts and other information. The diagnostic system obviously can be either rule-based or it could be probabilistic using a Bayesian belief network or something like that. But we believe really it does not truly matter. What matters is that you have optionality within the diagnostic model system. In terms of the way how we go through the model configuration and how we think the model configuration should run, obviously you've seen a similar chart from my colleagues in the presentations previously, but you have the signal that comes in, you pre-process it, you validate it. It's then pushed into first principle and thermal performance models. If it's going into maybe a data-driven model, you might do some sort of threshold check or something like that. And then it's fed into what we call APR. APR is a specific algorithm that we use. There are other algorithms that we use, but I'm using APR here for this example. And then obviously out of that, a data-driven approach, you might get a fault alert. You combine the fault alert and the performance models together in an ensemble, and then you generate essentially your final fault alert. Within the APR pattern recognition process, obviously there's a place where you have to define your blueprints for different types of assets you might come across. You need to select your training data. You need to have tools that does your EDA, exploratory data analysis, where you train the model and tune the model. Then you also need to validate the model during the process of conducting model testing and refining the model, and then deploying it, whether it's within your system or another system. Now, a few things, I might have to skip over some of these, but in general, out of this comes an anomaly. You might detect an anomaly if it's a data-driven model. And that anomaly, all it's there to do is to give you a very good idea. One, there's something wrong, and that it alerts you much sooner than your typical alarm system. We all have alarm systems, but the sole purpose is to give you an early warning indication that something is going awry. The secondary purpose is to essentially try to identify the problem, where that is happening. So that's what we tend to do. And those anomalies can be instrument related, it could be process related, they could be environmentally or energy related. It just depends on how you're actually looking at the models in terms of using performance models or data-driven models or mechanical health models. So just examples of these types of models. So thermal performance models, first principle models, those are examples on your left. You might have compressor models looking at your polytropic efficiency, your operating head, your operating power, your anti-surge valve opening duration, and things like that. Steam turbines, you have those lists. And induction motors, you also look at motor efficiency and motor load. We also work with third parties where you can even start to look at the voltage and the current to analyze anomalies in the voltage and power signal. Okay. From a heuristic standpoint, these are just SME rules. You know, a subject matter expert might say, I know that if this variable is this and this variable is this, is most likely possibly going to have a problem in a certain amount of time or something like that. So those are purely heuristical models which can be built by your people from the massive amount of experience that is stuck within the heads of your subject matter experts and operating staff. So in closing, this was an example. This is a site, a Honeywell site. Actually, we call it eating our own dog food. We took the technology that we developed and applied it to our polymer operation. And what we actually observed was a significant improvement in our operation. About, let's say, 2% revenue increase, which was typically directly related to the capacity that we added due to the unplanned shutdowns we were experiencing, and the operational increase of about 3%. Some key things about the solution: this solution was not placed on site. It was placed in the cloud. So again, eating our own dog food, a lot of customers are concerned about cloud deployments, but if we could actually do it in a secure manner on our facility to show our customers that, this is a viable and secure technology to be placed on the cloud and decrease your overall cost, capital expenditure, that's what we wanted to do. And that's what we did here. Cloud implementation, we produced reliability dashboards. We had embedded site-specific knowledge from the experts who run this plant for years and years, which essentially translated into ACP descriptive analytics as well. The total time to value, was about 6 months. And right now they're thinking about the next phase, which is an expansion of the solution at the site. So that's the presentation, hopefully on predictive analytics. Hopefully I'm right on time. And with that, if there are any questions, I'll take them and then I'll run into the second presentation.
Okay, thank you. Thank you, Ron. I think we have one question from Krishna. Krishna is asking if Annual is having SAP connectivity.
Yes, depending on your full requirements, because typically when we deploy an APM solution, it normally goes in with a lot of other solutions as part of a manufacturing execution system. So we would provide connectivity using what are called an ETL layer, middleware layer. Typically, we use BizTalk for that purpose. However, we also do have another solution, which I'll be talking about after this, is the connected worker. So this is the part where the person is actually interacting with the system. That has a standard interface to SAP. So yes, we can create one if and the ETL layer that we would use would be a Microsoft BizTalk for the middleware integration.
Great. Another question from Joachim Baptiste.
Looks like from Sabic, from Joaquin, says for RUL prediction models, do you use steady state or transient states?
You have to normally use transient state when you're actually looking at generally ruler. And ever so often you have to most likely, there are many ways how you can do the prediction, but the general way how we tend to approach it is what we call the general path method, okay? And that you have to constantly look at essentially the declining residual or the increasing residual of your expected versus actual performance to estimate your ruler.
The question is, would it be possible to provide a private cloud infrastructure for IP reasons?
Yes. In fact, we can do that. But obviously, with every additional layer of uniqueness, there is, a small additional cost. So normally we'd use public clouds, which are multi-tenant, so no one actually can access those. But you might even have your own data center, and within that data center, we could place it there. But obviously, you lose the economies of scale when you start to deploy massive amounts of hardware requirements if it's a very large project on your premises. But that is possible. We can do on site. The great thing about the cloud deployment is that you really don't have to worry about software upgrades, because the software upgrade is embedded within the service that we provide, and it's seamless to the user. So as soon as a new update comes, you might not even notice there's an update that flows to the system. So that's the beauty of the cloud system.
Thank you, Ron. You may proceed with your other presentation.
Yep. The second presentation I want to touch base on is what I call worker productivity. This is something that is quite significant when it comes to digital transformation, because essentially, I think of all of the things that we can do in terms of digital transformation, this is one area we tend to neglect. We tend to neglect the workers when it comes to tools that they need to improve their working conditions in terms of how productive they are. So within the agenda, I'll quickly go over the industry workforce productivity challenges that typically I think SABIC and many other companies face. Take you through a typical day in the life of a field worker. Give you a vision of where we think the future of the field worker actually is going towards. Identify some metrics around the sort of productivity that you can see from implementing these sort of digital transformation tools. Look at essentially what I call the cross-industry end-to-end visibility and the platform enablers that will allow you to justify things like this. Because this is a solution that does not only apply to chemicals, petrochemicals, we apply this solution throughout our complete value chain, our customers' value chain. And I'll get to those when I talk about it. And then I'll talk about two key focus areas around workforce productivity. One is around a software platform called Inspection Rounds, and another is around both a hardware and software platform we tend to encapsulate as worker assists. And then just mention something about the hardware paradigm shift that we see going on with all the connectivity that we see and the capabilities around natural language processing and things like that. And then have a quick Q&A. So as I indicated, your most important resource is your people. And I think you realize it because, as I indicated when I started, safety is number one. And safety essentially protects people. Without your people, your organization will not be able to run. So the challenges that we see today from an industry perspective is that we need to improve the field work efficiency and what we call the tool time of your field workers. We need to be able to give your field workers the capability to capture and manage what I call transfer of knowledge between workforces, someone going off, someone coming on, or someone leaving the organization and a new young, whippersnapper joins the organization. We need to also look at how we build and develop the skills with your people as they do their jobs on a daily basis, whether that means using augmented reality or things like that. And we need to actually provide a very interesting and challenging environment where we're using very, very good cutting edge tools within the environment to retain staff. Because we have a new generation of people coming up who are connected always. And if they're not very happy within the job because you're viewed to them as an old school type of operation, they may not stay there as long. So it's important that we stick with the technology so that we retain the people and train the people who we have. So those are the sort of industry challenges we see around the connected worker. Around workforce productivity and things like that. And we're quite sure that you're aware of these in terms of what's happening. And you most likely are trying to look for a work plan that will actually address these sort of issues. Now, in terms of the field worker is one of the last people we ever think about when we talk about manufacturing excellence systems, integrated refinery information systems, operator advisory systems. All of these are digitized solutions for the operators, process engineers, managers, maintenance management, but we never ever give them the tools to do their job succinctly. It's the most manually driven process right now. And there's a significant amount of what I call task management that comes into play when you're looking at the work order creation and scheduling and tracking of the field worker. So that's one place we need to improve. The generation of the work order creation, the scheduling and tracking needs to be digitized. Once that person has been assigned and they're out in the field, we need to actually give them the tools to be able to move from a paper-based system to a digital system. So whereby when they're in the field, they can essentially record the information as they go along, and essentially that information just streams into the connected systems that you have within your facility, whether that is a historian system, whether that is a safety compliance system or emission system, you name it. Once they're out in the field, there will be issues where they come across that they need some additional information. It's important that we have collaborative tools where that person is in the field, they can immediately hit a button and be in contact with the operator or some subject matter expert in the administration office. So, we have things like Skype, we have Zoom, we're using WebEx today. All these tools have some basic building blocks which might be efficient to providing to the field worker so that they're in a better touch with the other people within the organization. Then you also need to provide them information typically that they would not see when they're out in the field. The only thing that possibly they will see is the field gauges that they can read a temperature off or pressure off or whatever. But they need to have a better contextualized view when they're out in the field. And that's when you need to provide them digital information to help them through that process. Once they're out in the field, you also need the capability to make them aware of the surroundings. And in addition, if they're doing any operation, they might need some additional information about documents. They might need some information about the standard operating procedure. And they should have the ability to bring up those documents in the field as they're walking around, refresh their mind about the task at hand, so that when they implement the task, they're more efficient and productive at implementing the task. So overall, there's a lot of gaps within the field worker activity. And we believe there's significant amounts of productivity improvements that can be made by organizations, which will indirectly affect things like health, safety, and worker well-being. So what we're all about is enabling the connected worker. We envision, the connected worker or the field worker in the future having a device. It can either be head mounted or a device in the hand. They're walking around. They have to have a task on it. They implement the task. If they're not sure about how to implement the task, they pull up a YouTube type system. Okay, and it's not going to be YouTube, but it's going to be essentially a repository of videos where they can refer to very quickly, understand the task at hand, even test their knowledge about the task at hand. A 2-minute video or a 1-minute video. Yes, now I know how to do it, and then they implement the task in the field. If they also want to have connectivity with someone, they could hit a button on the system and immediately they could start a video conversation where they're talking to a subject matter expert. He's explaining what he wants, what needs to be done. He can even show him what he's seeing within the field. So it's about bringing all that connectivity that we all use today in our everyday life to the connected worker in the plant. It can be done. And that's our vision of the future, where the field worker essentially is using all the technology that we in our everyday life use within our daily task. Now, there's a significant amount of benefit to doing this because we've done some voice of customer analysis, and looking at projects that we've implemented, and just the savings, time savings, moving from a paper-based system to a digital system is about 60% improvement. In terms of accelerating the resolution time, because they have access now in the field to documents, real-time information, and can be able to touch subject matter experts either through audio or video to show them the problem that they're having in the field, we believe they can reduce the resolution times by about 15%. Now, in terms of the end-to-end, this solution does not only apply to petrochemical. It applies to oil and gas, it applies to manufacturing, it applies to mining and minerals. We're deploying this everywhere within the industry because it addresses about 4 main points. It addresses workflow digitalization, it addresses remote assistance benefits and provision, it addresses real-time access to data, and obviously, lastly, situation awareness. And the system is cross-platform agnostic. In that sense, what I'm talking about is that it can either run on a tablet, it can run on a headset, video headset, it can run on your telephone. Any platform that you have, form factor, it can run on it. It's ubiquitous. It uses 5G. It can use Wi-Fi. It can use Bluetooth. It uses all the connectivity standards that we use out there right now within our daily life. And the Bluetooth, the NFC, and the RFID is mostly for asset tracking and asset identification. The 5G and the Wi-Fi is mostly for the connectivity and the video conferencing that you might need in the field. So there are two areas we believe that workforce productivity has some significant growth and opportunity within our customers. We believe it's around inspection rounds. This is the digitized workflows, moving from a paper-based process to a digital-based process. And then there's also what I call the worker assist, where this is a combination of hardware and software. Hardware whereby the operators in the field now can wear head devices, free up the hands to be more dexterous within the field and do the task more efficiently and more precisely, and not avoid, safety or health incidents. So I'll quickly take you to those two. Inspection rounds purely is around orchestrating field operations, seamlessly integrating with your SAP system or your IBM Maximo system, standard connectors, dynamically evolving and essentially allowing you to deploy this system on almost any device that you want, whether it's a telephone, whether it's a Android telephone, whether it's an iOS telephone, whether it's a proprietary intelligent wearable. That's the head device we talk intelligent wearable. As I indicated, about 60% improvement in standard workforce processes we have seen. Okay, and I think this is in the presentation. I'm sure this will be distributed, but I'm trying to save time, so I'll skip through. The impact of this sort of technology is throughout the organization. I mean, it's thoroughly throughout the organization. It can be the reports and the information collected by this sort of technology can be embedded within your logbooks, your shift handovers, and things like that. It can be embedded in your historians, so you now take manually collected information and you digitize them into temporal data that is online, always available to anyone within the organization. It matches and can coordinate with your limit repository, which holds all the limits for your plant, safety limits, process limits, optimization limits. It's there, okay? It allows you to standardize your operations, whether those are related to maintenance or inspections or shutdown and startup. So you can even put startup and shutdown procedures on these devices for the operators to take out into the field. And even when you're in a maintenance turnaround mode, there is a place for using this system as well. So it cuts straight across the organization, and it taps almost every part of your business. What you have to have is the imagination of how it can be used, and then see how to efficiently deploy it with our expertise. These sort of systems have to be cloud-based, because that's how we upgrade the software, provide you continuous evolution in the software platforms and things. But they can be deployed on premise. That's not to say that it cannot be deployed on premise. But I myself, if I was a customer, I would say deploy it in the cloud, because I know I will have my updates very fast. I don't have to worry about maintaining hardware. I'm very confident that the system will be able to, the support mechanism behind the system is there, and I don't have to have a major support capability on site. Okay. So the second area is around worker assist, and this is where we use the intelligent wearables. And there are about, let's say, 3 or 4 main applications or value propositions around the intelligent wearable. We all think most likely this might be Star Trek-y, but it's here. We're using this sort of stuff right now. I can't imagine, most likely when Google Glass essentially debuted a couple of years ago, but they took it away for privacy issues and some other development. But this capability, this technology has proven itself, and it should be used within the plant continuously. I mean, there's so much value in terms of, one, just having the operator being able to be free and being able to have access to information in the field when they need it, depending on the situation at hand. It reduces time of task in the field, it improves team collaboration, it minimizes human error because you can actually check, the person can continuously check their knowledge in terms of how they're doing tasks and things like that. It closes the loop between the enterprise and the field worker. And obviously it can scale very easily. So within the worker assist environment, there are several key things I want to talk about. There's the seamless collaboration. And this is where we either use cellular networks, you have 5G right now, which will be 100 times more capable than our existing 4G and LTE networks. That means we can stream video significantly faster. And this is the sort of stuff that will enable that field worker to be able to be more productive and more safe. Whether you want to use the cellular network or Wi-Fi, that's up to you. If you have a very good mesh system within your plant, obviously you might want to use the Wi-Fi for security. But there is nothing making the cellular networks less secure. They're, in fact, I think, sometimes more secure. There's the access to information. Again, the system is just like a computer, but it's a computer on your head. So if you need to access a library of documents, you have that capability. You need to access a library of videos, you have that capability. You need to see real-time information from your historian or other visualization system, you have that capability. So it needs to be agnostic in terms of, I shouldn't say agnostic, it needs to be pervasive in terms of connectivity to different data sources. Contextualization insights, obviously, having trends and things like that to support the operator. I'll skip through these. And the last part is really talking about the device itself. The device should be explosive proof because we're all working within your environments. Your environments, SABIC environments, are explosion proof environments. So we need to have this to have the capability to be either explosive proof or non-explosive proof. It needs to also be driven by natural language processing. You should be able to talk to this device. You should be able to say, bring me up the standard operating procedure on pump 6556. That's how we envision, and this tool is intended to be used. So this is an example of truly a software ecosystem coming together with a hardware ecosystem of the future to actually enable the connected worker of the future. And we believe there's significant value that companies can get out of this. They just have to have the vision of where this can be applied within their organizations to make it a reality. With that, I think that's the last slide. Thank you very much for your attention. I know most likely it's end of day and we may have lost a few people, but really much appreciate your attendance and your attention.
Thank you very much, Ron. Very informative presentation indeed. Very great insight. We have a question from Krishna. How to handle will surely lead to downsizing of workforce. So who's worried about this? So
yes. That is always the case. When new technology comes, we really think about downsizing, but it's actually opposite. What happens is that you don't have a downsizing. They want us to do a little bit more. So our productivity has to go up. Okay, so I can understand his apprehension, but I don't think if that was the case, with every technology that we develop as a human race, we would always be concerned about this. There's a natural process that happens within the laws of economics and things like that, that there will always be an opportunity to move people from the jobs that they're doing right now to other types of jobs. So I say look on how the benefits are there for the organization, and through those benefits, productivity, and through increases, what more can that operator do in the field that normally he would not be doing because he was so busy doing other things before that he couldn't get to. So, that's not to say that I do not, concur with the sentiment. I believe that sentiment is right and it should be expressed, and that's part of the cultural change process that needs to go through, that an organization needs to go through in implementing these new technologies.
Clear, very good answer. Thank you, Ron. Any further questions? Since we are not having any further questions, again, I'd like to thank you, Ron. And if you have any questions, please save them till the end of this session. We'll have 30 minutes at the end for open discussion, or you can email the presenter. Now we will move to a very interesting presentation. We'll move about the application of Internet of Things and the use of digitalization for monitoring of materials degradation. Our last speaker is Dr. Praful Sharma. He is the founder and the Chief Technology Officer of Corrosion Radar, a very recent company in the corrosion monitoring of corrosion under insulation. Praful brings vast industrial experience, especially in digitalization of corrosion management, in which there are several inventions to his credit. Thank you, Praful, for accepting our invitation, and we are looking forward to hearing your presentation. The floor is yours, Praful.
Thank you, Abdul Mohsen, for the invitation and for the opportunity to present. Just a quick check. Are you able to see my screen?
Yes, we do.
Great. So I'll progress further. I understand this is the last presentation of the day, so I will keep it crisp and short, but very entertaining. Over the whole, and we can see Abdul Mohsen also being very diligent. He needs at least a coffee now, a kava, maybe. The whole day we have been there, and I saw great presentations from across the globe, different companies about digitalization. And there are various aspects of digitalization. There are various applications of digitalization. So what I will be talking about is using corrosion monitoring. How can we digitalize process? And this is a very big use case of digitalization. So my name is Praful Sharma. I'm the Chief Technology Officer of Corrosion Radar, based in UK, speaking from Cambridge right now. It's still daytime, so that's great. But people who are tired, let's start with a story. The story of Rob, Bob, and corrosion. In fact, it can be anyone. It can be Abdul Mohsen and Brian and corrosion. So say Rob is a manager. He asks, what is our biggest asset integrity issue? And Bob says, Bob, it is corrosion. Corrosion under insulation is among the biggest. Now, this is a very specific example, but in general, corrosion. Don't we have coatings with 20 years of lifespan, watertight insulations, reliable NDT and RBI practices? Management always asks these questions that we have the best of the best, but still there's a corrosion problem. There's a corrosion and insulation happening. There are leakages. There are limited budgets and resources. And then there are unplanned shutdowns. Bob, unplanned shutdown. We again found a leak. Oh no, how can we increase the budget? Should we look at the budget or look at the new technology, NDT technology, or should we look at the new processes? Now, I'm sure a lot of us can relate to this process because we are firefighting in the plants and balancing between budgets and technology and always looking for technology. So it is a pain. The problem which we are trying to say here is the hidden corrosion. For example, it can happen in petrochemicals, oil and gas, or any other industry. And corrosion under insulation is one of the big examples of hidden corrosion, but there are several other examples as well, like corrosion under pipe support. Now, why we are talking about it? Is it not a detection or inspection problem? But the reason why we're talking about is there's a huge mega trend, and I'm sure just the previous presentation, Reno talked about inspection 4.0, and we agree to it. It's a mega trend. We see inspection 4.0 is the new era of inspections, which is more automated. It's more automated. It's analytics driven. It's predictive. So we are moving, the whole industry is moving from manual to automated processes, detection to prediction, and reaction to prevention. Inherently, we see corrosion as a predictive problem, and we can use data, or people can use data to actually predict it and mitigate it in a better way. Of course, prevention is better than cure. So coatings, etc., they come handy. But at the same time, there's no foolproof solution to avoid corrosion. So data-driven solution. So there's a huge opportunity for the whole industry to go towards predictive corrosion management enabled by IIoT. Now, I would like to introduce this term to the audience who don't know this. IIoT means industrial IoT, industrial Internet of Things. Basically, a new paradigm where the sensors are becoming more and more available and cheaper. They have wireless connectivity with battery-powered devices, and they are being used in analytics on the cloud. So there's a huge movement towards IIoT for industries and use of predictive analytics, as we have seen some of the presentations today. The current practice in corrosion management is a lot of manual processes are there. For example, there's a lot of human judgment. There's a lot of dependency on the experts to estimate where to do inspections, where to do guesswork. So that leads to periodic manual inspection. It may be proactive, but it is not predictive, but it's maybe proactive periodic manual inspection. And then it leads to NDT and leads to RBI processes. Many times it leads to reactive, very not a foolproof solution, resulting in shutdowns, resulting in leaks sometimes. But going forward, I think inspection 4.0, we are moving towards predictive maintenance, where the use of sensors and connectivity and the use of knowledge base and analytics combined together to automatically identify the risks in a very early phase and then schedule the maintenance willfully rather than due to unscheduled shutdown. So scheduled maintenance is much more cost effective, minimizing labor and increasing the safety. So this is the paradigm we are talking about. And we identified the first application of predictive corrosion management being in corrosion under insulation. A lot of geographies are suffering from this. Some geographical locations are more suffering than others. But oil and gas industry and petrochemicals, they have identified CUI as among the top asset integrity issues. If we talk about static equipments, not the rotating equipments, and majority of pipeline failures are due to CUI. It's become a nightmare for the industry. The pictures which you see here are from Southeast Asia, a publication which from a large oil company which publicized this, but there are many such publications and pictures on the Google. It's a matter of just Googling in the images and you can find a lot of these. Basically, corrosion which is happening on the outside surface but remains hidden. Now, how this happens is when the water in the insulation unknowingly goes in due to rainwater or condensation, it starts to corrode at unpredictable locations on the outside of the surface. So to mitigate this proactively, people remove the insulations every few years, very manual process. How can digitalization remove this manual and make it more automated so that it becomes directly maintenance rather than inspection? So can we eliminate inspection altogether? So, corrosion radar is one of the systems, but this is how the industry is moving towards predictive CUI monitoring, predictive corrosion management, and these are the typical components of a of a typical system. So on the left-hand side is something detect, which is more of a sensors. So in this case, it's moisture and corrosion. In the middle is connect, which is the electronics, which is using the latest industrial IoT protocols to transmit data. And on the right-hand side is predict, which is more of software and algorithms. Now, these are the components, typical components of an industrial IoT system. So let's talk about the first one, which is more of example of a system which is sensors. So in this case, orange colors are showing the sensors which are embedded inside the insulation, pretty much installed like a heat tracing system, for example, in this case. And once the sensors are installed in a green field or even a brown field, in the brown field, it will be installed at the time when the inspection or turnaround are happening, when the insulations are already getting removed, so that you don't have to remove the insulation just for sensors. But for the green field, for the new pipes, it can already be part of the design. And they get installed at the layout of of choice, helical, it can be straight length, or it can be mesh, or even critical areas around the tanks. And both corrosion and moisture sensors looks and feels very similar, but they get installed, and sensor length up to 100 meters with one electronics can be covered with a wide temperature range. And from then on, the data gets transmitted and visualized on an analytics dashboard. I'll come to that in a minute. Where does it sit? But visualization and analytics are a big part of it. So as far as predict analytics platforms are concerned, these are examples we have heard from the past speakers today, that cloud platforms are becoming the norm. But a lot of oil companies and petrochemical companies have still policies around not sending the data to the cloud. So there's on-premises softwares are also available where the data can get shown. But going forward, I think digital twin platforms are getting developed, and in fact, we also have developed. We have demonstrator of working with digital twin companies. Digital twin is designed, described in many ways, but in this case, we are like Aspen in the earlier. Digital twin is a model, predictive model. But many companies define digital twins as kind of predictive 3D models as well. Even just a visualization with physics embedded in them. So in this case, we mean that we showed the data in 3D aspect with predictive models in place, so that you can directly go to the location where the red dots are. Now, these are the platforms for software. But at the bottom, you see different algorithms which are being used. For example, analytics modules, a prediction of corrosion rates from moisture sensor, for example, and even dynamic risk-based assessments. Now, dynamic risk-based assessments is a bigger deal, which I'll talk about in more details in the next few slides. So as far as prediction algorithms are concerned, I think this goes to more of corrosion engineers, but how can we use sensors to solve very dirty looking problem, which is removing the manual process of finding these kind of corrosions. And we continuously evaluate that in the lab with third-party labs as well, and match it with industry standards. Like industry have come up with standards of API 581, which locates which quantifies that what moisture means to the pipe, how much is the corrosion rate. So these are kind of going into the decision-making tools. The other algorithm, and we are very excited about, and it's a very good example of digitalization, is enabling dynamic risk-based assessments. Let me spend a few minutes on this. It's about optimization of inspections. So risk-based assessments, or RBI or RBA, they are the industry standards. A lot of companies use it, but they are fairly static. On the left-hand side, you see the static RBA process is year 1, year 5, and probably year 10 will look very similar because they are not updated. In this case, for example, a risk matrix is there, consequence of failure, probability of failure. These are the standard ways of looking at it. And here is an example of 3 assets, asset 1 to 3 of different risk profiles. The moment they are risk analyzed in year 1, but the inspection is scheduled in year 5, you're still making a decision of inspection based on what was year 1. It's not periodically updated. It's not reflecting the field conditions. But in effect, in the dynamic RBA on the right-hand side is a new paradigm, which we are trying to say that you need to update the risk automatically, dynamically, with the sensors in place. So this is an example of sensor-driven automatic risk analysis, where periodic updates are done. It can be done from the sensors to manually feed into the RBI softwares, or it can be automatically connected. And it incorporates field conditions. For example, in API 581, the moisture sensor, the moisture information is used to find the severity of corrosion rates. And in this case, you get the same data directly from the field on the moisture sensors and update the risks. So in this case, for example, asset number 2, which is low, in this case, probably water is detected, so it went high in the risk. But if there's a very high risk already identified for an asset, but there's no water detected over a period of time in 5 years or 10 years, this need not be inspected at all. So the risk probability of failure have gone down, cost savings. So there's a huge benefit in risk-based assessments for CUI, making it dynamic, and industrial IoT sensors enable that. Not only our systems, but the other sensors can also do that. The other, sorry for the slide, I think the title is a bit embedded here, but the key point here is the higher resolution of risk. Now, this is another example of digitalization, the benefits of that not only on the left-hand side, you see the current status, say in the current method, the static understanding of the risk, the whole asset is at the same risk. For example, in this case, 10 meter of pipeline is the same color coding, it's very low, and over time it changes, right? So this is the usual process, but in effect, this is very inefficient process because the risk can be very localized. So on the right-hand side, what you see is the same pipe length of 10 meters, the granularity of risk is segmented into half a meter length. And if you see at the year 7, 84 months, that particular length is showing high, that particular segment of 2.5 to 3 meters is high, but everywhere else is low. So compare that scenario on the left-hand side, which is very high all over the place, which means you have to inspect everywhere, the whole pipe. Now scale it up to 100 or 1000 meters, this becomes a very inefficient process. Compare that to the right-hand side, which is only that one particular meter it needs to be inspected, which means scaffolding only in that meter, huge cost savings, and probably safety savings that if this is not inspected in the right place, there might be a mishap, leak. So it's important to identify the right location as well. So these are the examples of benefits of monitoring systems and outputs. I'll quickly talk through some of the case studies. For example, case study A is production column. Now, this production column was manually inspected. This is in Netherlands, 25 meter high. And this was manually inspected every few years. Huge cost in scaffolding, etc. And then the operator decided to move away from periodic inspection to condition-based inspection. So condition-based inspection means you need to know the condition, you need to monitor. So these sensors were installed on the top and the bottom, the orange colors, and then they were connected to the electronics in the middle. And then from then on, what is happening inside the insulation is being monitored. Now the idea is, it's been a few years, I think few years on this already. The idea is if moisture is detected, they will inspect only a particular location where moisture is detected by a rope access, which is much cheaper because you'll know precise location. But if moisture is not detected or corrosion is not, corrosive conditions are not found, they will skip inspection cycle and save cost. So hopefully that happens. Here's another case study, which is more of a moisture sensor. The most important is the figure D, which is showing the moisture sensor now. The moisture sensor was placed below corrosion sensor in this case, but it can be embedded near the corrosion sensor. But in this case, the operator decided to put it right outside of the insulation to put cladding over it. And the physics of this is the water goes in and settles at the bottom. So this is the most likely location of water detection. Now in this case, wet insulation is the condition which wants it to be detected. So here the data looks like the x-axis being the date and the y-axis being the distance. And in this case, around 22 meters location from the electronics, there was an interesting pattern observed where the water was detected and there was periodic drying and wetting cycles. And this was highly correlated with the rainfall. So normally in a manual process, non-digitized process, people will go the whole pipe, open up the insulation every few years to inspect. But in the digitalized case, this data will be analyzed remotely and say, okay, at this particular location, there's a drying and wetting cycles, which are very risky for the corrosion, very risky for the coatings. This location needs to be prioritized for inspection in the future. So that's the new paradigm of decision making with digitalized tools. Again, other case studies, I will skip that for the benefit of time. But in this case, there's a complicated pipe network with a high probability of CUI observed earlier. So the end user installed a sensor and then monitored over time. So after 7 months of the monitoring, they observed that, this is the raw data. So let's not go into the raw data. We have algorithms to detect where the corrosion and water is. But on the left-hand side, if you see the 3D models, the corrosion was located at the top and the water was located at the top and other locations. So normally in the normal manual circumstances, people will not know this information. They will have periodic opening of insulations, create scaffolding. But in this case, now they know that there's water coming in. They will exactly know where to open it and do even non-intrusive inspections. So safety and cost. Other case studies on pressure vessel. For example, in this case, it was confidential, so we are showing you a mock-up of this. That this is a pressure vessel which was mandated and regulated to be inspected every few years, to be inspected even if something is there or not. So the operator convinced the regulator that you can put a sensor in, put insulation around and start to monitor, and if there's no water, there's no need for inspections. So it's an ongoing exercise. The data is being monitored on the cloud-based dashboards, and if there's no water, there's no inspection needed kind of philosophy to save costs and increase safety. Another case study on LPG pipeline, cold pipeline, and I particularly like this because this is uninspectable pipeline, because this is operating at minus 45 degrees Celsius. They can't manually inspect it. But how digitalization can help here is if you put the sensors, which in the case of here helical, and there was a kind of test section created just in the early phases to prove the concept at pilot. So at the commissioning, this is how it looks like, but the end user, just to make sure that before larger scale rollout, they are sure that it is working, they created this dummy pipe section and they corroded it over time with very severe forms of corrosive solutions. So after 6 months, it was severely corroded, and we could see that. What happened with sensors is it detected water whenever they injected water. So x-axis being the timeline and location being 18 meters here along the sensor. And the corrosion was also detected after 6 weeks of commissioning, which means a very aggressive early form of corrosion. Now this proved the concept as well as in this location, as well as it showed the algorithms showed that the risk-based assessments, there's a change of risk from very low at that particular location to high within a few weeks. Normally this will be very low, continuing to be very low if the data is not available, and they will wait for a few years to manually inspect it, and it's very risky. So you see how digitalized way can help in actually materializing the benefits with industrial IoT monitoring sensors. So I would like to summarize here before taking question and answers is digitalization with predictive corrosion monitoring. It's more about this use case about CUI, corrosion and insulation, but similarly, the takeaway for you is any other forms of corrosions are also similar beneficiaries. I mean, any company can do that when they make a specialized sensors, but the paradigm is corrosion monitoring, and it's not only about corrosion, but also parameters surrounding the corrosion. In this case, it's moisture in the insulations. So it can lead to more data-driven risk-based assessments, dynamic RBI, optimized maintenance, or if the RBI process is not existing in the company, it can be even early detection to reduce unplanned shutdowns, leading to predictive maintenance, cost savings, and risk reductions. Our case studies have shown, depending on the type of asset and the location, offshore, onshore, it can lead to anywhere between 25 to 65% of cost savings, mainly because the inspections are now being done at a very targeted, focused level rather than widespread level. And also safety is increased. So prevention is better than cure. So this can lead to prevention as well. If you know where the water is coming in, you can do an inspection early on and actually take mitigation steps of any leaks and seals. You can seal it off and even extend the life of the asset. So I'm happy to take question and answers. Hope this was useful at the end of the day. Very fast paced. I went faster than my speed. So apologies for that, but I'm happy to take some questions.
Thank you, Prof. All, for a very great presentation. I personally enjoyed the presentation. I am very confident that all enjoyed the presentation. We had some questions, maybe you would like to highlight and comment on them. They were mostly related to calibration and sensitivity, temperature range of sensors. So it would be nice if you could highlight these things.
Right. Sure. I mean, I'm having trouble in seeing the questions. Can you start reading them and probably I'll answer them?
Yes, I can. So there was a question for the possibility of sensors calibration, I mean, internally. And there was another question on the temperature range for the sensors. A third question was on the, do we have to wrap the whole pipe or a selected area? This is from Raid Zaini from Yansab, and we are actually implementing a trial at Yansab of corrosion radar. So you may refer to your colleagues at Yansab for, for better evaluation of the system, in practice, because the system is already there.
Right. So there are a few questions on this. So let me answer the first one, the calibration. So once the sensor gets installed, the first data is the baseline, because the sensor can be affected when the installation is happening. But once the installation happens and the installation is in place, we treat the first few data sets as the baseline data, and that's our calibration. And after that, we don't need to do it. It's more of changes which are observed. So that's on this particular case, but I'm sure moving beyond our company, there are many other types of corrosion, and they follow the similar pattern of taking a baseline initially and then observing changes. So that's one. On the temperature range. At the moment, we have up, this particular case, it's 300 degrees Celsius maximum. In this case, UI normally happens up to 130, 40, or even 175 degrees Celsius, because water evaporates, it gets trapped. So it does not corrode if it is too high a temperature. So CUI is a particular problem below 175 degrees Celsius. But our sensors last up to 300 degrees Celsius. In the cyclic mode, if the temperature exceeds, the sensor should survive. On the negative temperature side, at the moment we have minus 50 degrees Celsius, going to minus 90 in a very short period of time. We'll be releasing minus 90. But LPG temperatures are pretty much within that range, but we are looking at LNG temperatures as well. LNG is minus 160, and we are working on a temperature for sensors for that. Now, you may ask that, okay, those are the temperatures at which ice forms. There's no corrosion. But the industry has observed corrosion for cold insulation, because the cold insulation goes through wetting cycles, batch processing, etc., where the water gets condenses when the temperature becomes normalized, system is shut down and it gets trapped. So the corrosion CUI still happens in the cold insulation, and this system can detect that wetness. The last question was from Yansab. I think the trials. I think I will skip that, because there's a good amount of information within the
Yes, indeed. Okay, thank you. We have further questions, actually. One of the questions is this an alternative to TSA? And the answer is obviously yes.
Yeah.
What is the sensor lifetime?
So the sensor lifetime, this is designed for going through many turnaround cycles. So typically the design life is more than 15 years for moisture sensors, and corrosion sensor is also more than that. But when the corrosion sensor corrodes, it's a sacrificial sensor. That particular location needs to be refurbished, or it can be left alone. That particular section where corrosion has happened, because other sections of corrosion sensor will continue to function as normal. But when a turnaround comes, probably that particular 1 meter section can be cut and then rejoined with a connector. It's modular system. So, but if it is not needed, it can be left as it is, for a long period of time. So that's how it is designed.
Okay. Any specific sensors for tank bottom plates?
Well, tank bottom plate is a very interesting application for monitoring and digitalization. We are evaluating it. I would say we have not used anything on that tank bottom surface for our sensors, but we are trying to understand the problem and see it. So if there are applications somebody would like to discuss, we are open to discussions and see whether we can apply to that. But so far, no.
And finally, we have a question from Tariq. What is the minimum detection limit?
Right. So this is not an NDT technique. This is not an inspection technique. This is more of a monitoring, and we are not detecting anything on the pipe. We are everything detecting on the sensor. So on the moisture sensor, the minimum moisture fraction we can detect, which is in the insulation, is about 30% water and above. So that's the minimum detectability limit for the moisture sensors. For the corrosion sensor, the way it is defined is what is the minimum thickness of corrosion before which we can detect corrosion, and that is about 0.2 millimeters. So if that 0.2 millimeters of corrosion happens within, say, 6 months, it will be 6 months. If it is aggressive corrosion within 1 month, we can detect in 1 month. But the idea is to have predictive CUI, which means detect CUI conditions early on so that you can schedule it many years in advance. Turnaround periods are decided many years in advance. So you don't want to detect it very late, but detect it early so that you know where the corrosive conditions are getting developed early on. So that's the minimum detectability limits on the sensors.
Okay, thank you very much. Any further questions specific to CUI or digitalization for corrosion monitoring? Okay, so it looks like we are having no further questions, and thank you, Praful. Actually, this is the perfect ending to give an example of how to utilize advanced analytics, and this will also show people the complexity of utilizing advanced technologies, and so not all of these technologies are very mature. So we see the development. So this is a recent development indicating that there is still an area for development for other applications indeed. And we expect to see a lot of developments in the near future. Now, if you have any question to any of the presenters, please feel free to ask your question. We have representatives from all participating organizations. So if you have any questions, please feel free to ask your question. We are getting one more question. It is back to Praful. It's about the connectivity of the sensor. So the question is, how do you attach the sensors to the pipe or the vessel?
Okay, so I can take that. And probably I'm inaugurating the question answer session of the end of the day. So yeah, normally it's installed very easily. It's like a heat tracing system installation. So you put the sensor on and then put it with some kind of local temporary tape arrangement before the insulation is placed. So basically insulation holds it in location, in place. But before the insulation is put, we put temporary ties attaching the sensor to the pipe, or even tanks and vessels. So it's not too difficult, and we follow the same practice as in the heat tracing systems. And I would like to go further in answering this. Is there are flanges and bends in the pipelines, so the sensor goes around the flanges and bends. They're protected in that location, but like a heat tracer system, it also goes around the flanges and bends and protected locally in that location.
Okay. Okay. Any further questions? Okay, so this is from Raidani about plant data. If the data is measured at a different scanning time and historized with different averaging time, does this impact model accuracy? So this is open for any of the presenters, and any of you could pick this question.
This is a question that always comes up when you're looking at predictive analytics and things like that. So it really depends. It depends on the asset that you're looking at. It depends on what sort of fault, most likely, or faults you want to determine. We have customers that give us 15-minute data, 10-minute data, 1-minute data. But what I would say is that you have to look at each case on its own. But generally, you can get away with 5-10-minute data. What I will be more concerned about is the fact of the historian. Okay, and let me explain what I mean. When you normally collect information and then you give, maybe you decide that you want to use 10-minute timestamps from data. There's most historians have a capability of compression, what they call compression, and and when they do compress, I've seen maybe a historian where you have a real-time value maybe coming in every 5 or 10 or 15 minutes, and then all of a sudden that value for some reason freezes. And then the data collection continues to go on, and then you get maybe a data point, maybe I don't know, 5 hours later, sometimes 1 or 2 weeks later. And what happens is that because the way how the historian picks the data out of the archive, it draws a line between the first point and the last point. And that creates a problem. So I would say that always look at the the situation, i.e., what you're trying to do, that will affect frequency of the data that you need, and also additionally make sure that your compression algorithms and things like that are very correctly tuned in terms of if you're going to be extracting information from the data historian. It should not make a significant difference, but I have seen some issues, but they're very minor issues. So be cautious. 5 to 10 minutes should be okay. If you're going to go to 1-minute data, obviously that's a large data set because you're going to be collecting very fast data. And also be cognizant of the data compression issues within historians, and make sure and check with your provider that it's not an issue.
Very, very good answer. Very comprehensive answer. Thank you, Ron. Another question. This one it is to Praful. Where do you see the greatest demand, appetite, and maturity in adapting predictive corrosion monitoring?
Okay, thank you. Yeah, happy to answer that. So, yeah, predictive corrosion monitoring is an example of digitalization. So, in general, what we see is the oil industry, petrochemicals, refineries, even upstream industry, they are under huge pressure of improving the efficiencies because of the low oil prices as well, low economy. So they're under huge pressure. So we have seen budget cuts in many other applications, but the budget increase in digitalization, so that's a counter trend. So within digitalization, now these companies, they always ask, okay, what are the use cases? So obviously earlier in the day, we saw this presentation that use cases are important, something which have got the highest tangible ROI. Also, safety increase. What are the low-hanging fruits? And we believe predictive corrosion monitoring fits into that category of low-hanging fruits, where it can be implemented quickly, and returns start to see where manual processes are being moved out and automated processes are being in. Where we see the greatest demand is suddenly, because of even before COVID and now because of COVID, hopefully everybody's safe in our community. But the companies are relooking at how much manpower we want to deploy in the field versus how much manpower, the same manpower, can do work remotely. We have seen examples today from Honeywell as well about remote inspections, right? If the data also comes to the desk, can we do the remote inspections? And that's where we see a lot of discussions and demands, pilots, where companies which are realizing that can we do the same thing, which does not need to go to the field, can we do remotely? That's where the greatest demand is coming. And I think oil industry, offshore, there's a big potential. Refineries, petrochemicals, there's a big potential. We are seeing a lot of interest from Middle East region, to be very honest. And the Middle East region is trying to embrace digitalization in general. Of course, we are seeing from various geographies, USA, a lot of discussions. But yeah, Middle East is a lot of discussions as well. So yeah, geography-wise, various geographies, including Middle East, and across the spectrum, I think there's a good appetite of adopting digital solutions, including predictive corrosion monitoring, especially in the era of low oil prices and economy. Back to Abdul Mohsen.
Thank you, Praful. I have a question, and any of the presenters are, welcome to address that question. And I would even prefer if more than one the speakers would address this question. So in your interaction with your customers in the petrochemical industry, do you see a variation in the appetite in adapting digitalization solution, or do you see some of the clients are more digitally advanced than others?
Go ahead,
Yeah, this is something that, again, I'm glad you asked the question, because there is a wide variation in the interests within chemicals compared to other industries, oil and gas, refining, things like that. And I think, we're all we're all suffering from a major, how would I say, downturn in the hydrocarbon industry. And that has put a lot of pressure on chemical and petrochemical manufacturers, not to even mention the oil and gas companies. So based on that, yes, we do see a little bit of how would I say, hesitation or slower movement from the chemicals and petrochemicals, but that's not because obviously the technology is not applicable. I think it's more to do with the economic conditions, but I think that is changing. Okay, for example, Honeywell last year signed the largest, I think it was the largest so far. I haven't seen one. The largest predictive analytics project in the world so far with the ADNOC group of companies. And that's for all the assets, So and that applies to also the chemicals, joint ventures and things like that. So I think that there is a small hesitation, but I think that will be overcome with time. There is interest out there. The chemical and petrochemical companies are looking, at this technology and these technologies. And I think as we go into 2021, I think we expect to see possibly a pickup in the interest to pursue these, whether on a proof of value concept or a smaller scale than some of these large deployments of predictive analytics. But yeah, a small issue, but not very significant.
Okay, thank you, great answer. Thank you very much. We have also Sridhar would like also to address this question. So could you please unmute him, Byron?
It was a great question. I think, I see what I'm seeing here, at least in North America, is that digitalization has become a way to address the significant downturn in the industry. And what that has meant is a lot of the big operating companies are looking at this as a way to really achieve more with lower costs, because one of the key concerns with conventional modes of operation has been that, safety and reliability has been a pretty expensive enterprise. And I think going into 2021, what we are seeing is a lot of interest in both prediction tools as well as digitalization as a way to improve efficiencies and optimize operations.
I would like to add to this and actually ask a question to Sridhar as well, since he raised the point about use of prediction tools. So, Sridhar, I mean, you mentioned about prediction tools, and in the North America, how the prediction tools are based on which type of data? Is it like, I talked about sensors, so that's kind of generating the data, but do you have examples of prediction tools without generating, without even installing hardware, and use prediction tool based on already available data or based on physics principles, etc.? So basically trying to understand whether there is a movement towards CapEx conscious. Can we do it without CapEx?
A great question. I think we are kind of at I would say, a point of inflection when it comes to having prediction tools that work in real time with process historians and process data. And what I'm seeing is that, and we've done some pilots recently, where we are looking at deploying some of these prediction tools that have been developed over the last, say, 15, 20 years to work like software sensors, right? So what that means is that you're not really investing in hardware, which is always a problem. In time, these customers don't want to invest in capex and don't have the funding to really spend, let's say, $200,000 on installing permasense or sensors. So the trend has been to really integrate our understanding of both process data as well as the correlations or the basic fundamentals of, say, thermodynamics, phase behavior, all those things, and to deploy these models closer to real time. See, traditionally, prediction models were used as offline tools. And what we are seeing, some of the big operating companies locally here in Houston, for instance, is that they are moving towards using these software applications as a way to help them identify hotspots, for instance. So when it comes to corrosion, you are less concerned with the exact corrosion rate. Like, I don't care if it's 3.75 or 4.2. I want to know if it's less than, say, 10 mils per year. And in those kinds of situations, the prediction models really work quite well. So that's really what we're seeing.
Okay, great. Thanks.
Great. Any further questions?
We did have one from Nina about for corrosion radar. Where are you using this technology? I'm not sure if that was for Prayful.
Well, I can be quick. So yeah, I mean, we are a Europe. There are some operators who are using in Europe, and we have deployments in Middle East as well, Saudi Arabia including, and Abdul Mohsen have already revealed that one of the users is Sabic as well. So yeah, we are happy to talk to you further and describe in more details. But yeah, keeping the spirit here is about digitalization. So happy to discuss offline after this meeting.
I think there are so many questions, and I mean, even the panelists, I assume they have also questions for each other. I like the question that was asked by Praful, because that's indeed a challenge for digitalization. the challenge of CapEx, and I would like also to take Ron's opinion on that, and if this will limit the digitalization in the near future.
Yeah, it's interesting that you say that, because this is one of the big why there's a big push towards using the cloud. Because when you go to a cloud type of model, you also have the possibility to change your deployment model, i.e., from a perpetual type basis, which we've always tended to assume, to a more subscription type basis, and depending on your internal procurement and budgeting restrictions, when you move to a subscription type cloud-based service, then you technically you should be able to claim that as an operational expense instead of a capital expenditure. So the idea of cloud enablement and subscription type models tends to support this need to move away from a capital expenditure budgeting type of paradigm to a more operational expense continuous subscription service model.
Okay.
I would also like to add here, in fact, if my colleague James is online, he can actually talk about IoT, industrial IoT models, which we are at the cutting edge looking at, like removing away CapEx to OpEx, because CapEx is always the budgetary constraints, but OpEx means how can it be distributed over a few years, use different types of IoT models. If James is online, if you can unmute James Rosenstein, so he can talk about some of the IoT models which we are observing in the market.
Okay, thank you, Praful. So I think it's very clear a lot of companies and consumers are moving to a more of a consumption model, pay for what you need as and when you consume value from solutions. So we are seeing a great interest in data as a service, and looking at the value in the data, and certainly the OpEx model is favoured to the CapEx model. Of course, with certain technologies, you can't avoid some upfront costs, but definitely we see the flexibility and the scalability in providing solutions like monitoring as a service, and that also opens up opportunities for companies to partner together. Someone asked a question about collaborating sensor information. If companies are able to go to a particular marketplace and acquire multiple sensors as a service, and these packages are simplified in the way, then this is definitely the way forward for a lot of companies. Hopefully that's answered your question.
Yeah, this is a very good answer indeed. Thank you, James.
I think, just to add, because there's a point which came out about collaboration, I think in digitalization, no single company can do everything in the world. So digitalization is a very fast-paced moving topic. And if one company starts to do everything, then it takes time for them. So the model which are evolving is collaborative models where companies are collaborating and providing joint solutions to the end users. For example, the wireless connectivity can be provided with one company who specializes in that wireless connectivity in the plants, and they are trusted partners. But the dashboard and data services being provided by some other company, the sensors being for different applications being provided by a third company, and all of them joined together to solve a problem. Imagine this in the past was done by one company. The innovation cycle was very, very slow, but because now the innovation is distributed among different companies, the innovation is faster and the solutions are being faster to the market. But collaboration is the key, I think, in the digitalization where different types of companies work together.
This is a very good point, actually. We see actually a lot of initiatives in the industry by different companies. It looks like some companies are trying to establish their own programs. We see also that some companies are working with some solution providers. So we see both, I mean, in front of us. We don't know still, I mean, it is not very clear that which model is the most successful, but both are existing in the market so far. We have another question from Raid Zaini. Raid is asking about the time it takes to build a twin for cracker, olefin cracker. Maybe, I don't think Pavel is with us. Maybe he talked about the twin. Or if we have someone from Aspentech, maybe they could also speak about this. Pavel, he left earlier because he said this is a public holiday in Russia. Today is a public holiday, so he could not stay until the end of the talk.
So we do have, this is Ronald from Honeywell. We do have a case where we've worked with a customer in India around an ethylene cracker, and the whole objective was to create what I call a machine learning health model to predict cooking in the ethylene cracker. We use combination of methods, but one of the methods that we used, which is quite interesting, was they had already built, or we had already built, what I call an OTS simulator. And we took the OTS simulator and used it as the input to the machine learning algorithm to build the health index. So that project, I think, took about, let's say, I think it was about a year, because obviously we had to correctly tune the simulator and make sure that the kinetics of the cracking process was all in line and agreed. And then the training then took place in the data gathering. So expect maybe about a year, but that's because, you know, obviously you're not starting from a point where you have the data. You have to generate the data, and that's why the time. That's why you have to have this a little bit longer time. But if the data is already in a historian, obviously then you can do your predictive analytics much faster because it's just a history retrieval instead of a history generation or a data generation problem.
Okay. Thank you very much, Ron, and thank you, Raid, for asking this question. So I think with this, we are coming to the end of this event. We would like to thank you all for attending this event, and we are very grateful for your effective participation and all the questions you've been asking. This was a very fruitful engagement. We would like also to extend our sincere appreciation to our presenters today. They have presented very great material. We are very grateful for them. Very informative presentations indeed. We already got the presentations from the speakers, and we will upload the material in the MTI website. So you can later on log in and access the material from the MTI website. Also, the recording of this event will be available in the MTI website. Again, thank you very much for your attendance and for your effective participation. Thank you, everyone, and we are looking forward to have you in future events. Thank you.